So there was no space, no time, no matter, no energy, no atoms, no light, no sound, nothing. And I don't mean the kind of nothing where you open your pantry and realize you've got nothing for dinner. I mean actual nothing. The kind of nothing that supposedly existed before the Big Bang. The kind of nothing that makes your brain short-circuit when you try to imagine it. Because here's the thing. When scientists tell us the universe exploded into existence 13.8 billion years ago from a point smaller than an atom, the natural question everybody asks is, okay, cool, but what was there before that? What existed before the Big Bang? What was there before there was a there? And the answer you usually get from physicists is some variation of, well, there was no before because time didn't exist yet. Which, let's be honest, sounds like they're dodging the question. It sounds like they're saying, shut up, stop asking, it's complicated. But here's what I've come to realize after diving into this topic for way longer than is probably healthy. They're not dodging the question. The question itself is the problem. Asking what came before the Big Bang is like asking what's north of the North Pole. The words make sense individually, but together they're pointing at something that doesn't exist. And that's not a cop-out. That's a profound statement about the nature of reality. But it gets weirder. Because as much as physicists will tell you the question is meaningless, they've also spent decades trying to answer it anyway. And what they've found is absolutely wild. Quantum mechanics, the physics of the very small, suggests that nothing isn't actually nothing. The vacuum of space, even if you remove every particle, every bit of energy, everything you can possibly remove, it's still seething with activity. And that activity, that quantum foam, might be exactly what gave birth to everything. So buckle up, because we're about to dive into the deepest mystery in all of cosmology. We're going to talk about what nothing really means, what the Big Bang actually was, and why the answer to where we came from might be stranger than nothing itself. The cosmic blank canvas, deconstructing nothing. So let's talk about nothing, like actual nothing. And I don't mean the kind of nothing where you open your fridge and realize you've got nothing to eat, or the kind of nothing you feel when you're scrolling through streaming services for 45 minutes, only to rewatch The Office for the 100th time. I'm talking about the kind of nothing that supposedly existed before the Big Bang. The kind of nothing that makes your brain hurt when you try to wrap your head around it. Because here's the thing. When we talk about what existed before the universe, before the Big Bang, before everything, we're not just asking a simple question. We're diving headfirst into one of the most mind-bending, philosophy-breaking, logic-defying concepts that humanity has ever tried to tackle. Now, I want you to think about nothing for a second. Close your eyes if you have to. What do you picture? If you're like most people, you probably imagine empty space. Maybe a vast black void stretching out infinitely in all directions. Maybe you're picturing the vacuum of space, like what you see in Star Wars or any sci-fi movie where someone gets sucked out an airlock. That's what most of us think of when we hear the word nothing, right? Just empty space. No stars, no planets, no matter, just emptiness. But here's where things get weird. And I mean really weird. That image in your head, that mental picture of empty space stretching out forever, that's not actually nothing, like at all. Because space is something. Space is a thing that exists. It's a dimension. It's a fabric. It's a structure that can be measured and bent and warped. Einstein proved that with general relativity. Space can curve around massive objects. It can ripple with gravitational waves. Hell, space is expanding right now as we speak. So if space is doing all these things, then space is definitely something, not nothing. So when we try to picture nothing in the context of before the Big Bang, we immediately run into a problem. We're trying to imagine a state of existence, or I guess non-existence, that our brains are fundamentally not equipped to comprehend. Because every time we try to visualize it, we default to picturing empty space. But there was no space. There was no emptiness to contain the nothing. There was just, well, nothing. And that's not just hard to imagine, it's basically impossible. Now, this is where people start to get frustrated with physicists and cosmologists, and honestly, I get it. Because when you ask them, what was there before the Big Bang? A lot of them will give you this answer that sounds like they're dodging the question. They'll say something like, well, there was no before, because time didn't exist yet. And you're sitting there thinking, cool, thanks for nothing, literally. But here's the thing, they're not being difficult or trying to sound smart. They're actually telling you something profound about the nature of reality that we've only really understood for about a century. See, before Einstein came along and turned physics on its head with his theory of relativity, everybody thought of space and time as these separate, absolute things. Space was just the stage where everything happened, and time was this universal clock ticking away in the background, the same for everyone, everywhere. Newton's laws worked under that assumption, and for most practical purposes, they still do. But Einstein showed us that space and time aren't separate at all. They're woven together into this single fabric called space-time. And this fabric isn't just a passive backdrop. It's dynamic, it's flexible. It can be stretched and compressed and warped by mass and energy. So when we talk about the Big Bang, we're not talking about an explosion that happened in some pre-existing space. We're not talking about a bomb going off in an empty room. We're talking about the origin of the room itself. The Big Bang is the moment when space-time came into existence. Before that moment, and I'm using the word before very loosely here because it doesn't really apply, there was no space for anything to happen in. There was no time for anything to happen during. The entire concept of before breaks down because before is a temporal term and time didn't exist yet. Let me try to put this another way, because I know this is the kind of thing that makes your brain want to shut down and go watch cat videos instead. Imagine you're watching a movie. The movie has a beginning, a middle, and an end. Now, what happened in the movie before the opening credits? Well, nothing, because the movie hadn't started yet. You could say the film was being loaded into the projector, or the streaming service was buffering, but those things aren't part of the movie's narrative. They're external to the story. In the same way, asking what happened before the Big Bang is like asking what happened before the movie started within the context of the movie itself. It's a category error. The question doesn't quite make sense in the framework we're using. But okay, let's get into what we do know about the Big Bang. Because despite all this philosophical hand-wringing about the nature of nothing and whether before is even a meaningful word in this context, scientists have actually figured out a hell of a lot about how the universe began, and it's pretty spectacular. The Big Bang happened approximately 13.8 billion years ago. If you want to be really precise about it, and scientists love being precise, it's 13.787 billion years, give or take 20 million years. Now, in cosmic terms, a margin of error of 20 million years is pretty damn good. That's like estimating someone's age and being accurate to within a few minutes. So we know when it happened, at least roughly. But what actually was it? Here's what the standard model of cosmology tells us. At the very beginning, at time equals 0, everything that would become the observable universe, all the matter and energy and space itself, was compressed into an infinitely small, infinitely dense, infinitely hot point called a singularity. Now, when I say infinitely small, I don't mean really, really small. I mean actually infinitely small, a point with zero volume. When I say infinitely dense, I mean all the mass of the universe packed into that point of zero volume, giving you a density that's literally infinite. And when I say infinitely hot, I mean temperatures that make the core of the sun look like a freezer. This singularity is where all the equations break down. General relativity, which describes gravity and the large-scale structure of spacetime, predicts that such a singularity should exist at the beginning of the universe. But general relativity also can't tell us what happens at the singularity itself, because when you plug infinity into your equations, you get nonsense out. Division by zero. Undefined terms. The mathematical equivalent of your calculator throwing up its hands and saying, "I can't help you, buddy." Quantum mechanics, which describes the behavior of matter and energy at the smallest scales, also struggles with the singularity. In fact, one of the biggest problems in modern physics is that general relativity and quantum mechanics don't play nice together. They're both wildly successful theories in their own domains, but when you try to combine them, when you try to describe something that's both incredibly massive and incredibly tiny, like a singularity, the math gets ugly fast. This is why physicists are so desperate to find a theory of quantum gravity, some framework that can merge these two pillars of modern physics into one coherent picture. String theory, loop quantum gravity, all these exotic ideas you've maybe heard of, they're attempts to solve this problem. But let's get back to the singularity. From this point of infinite density and temperature, the universe began to expand. And I want to be really clear about what expand means in this context, because it's another place where our everyday intuition leads us astray. The universe didn't expand into something. It's not like the singularity was sitting in some larger space and then started growing into that space. The expansion of the universe is the expansion of space itself. New space is constantly being created between galaxies, which is why distant galaxies are moving away from us. They're not flying through space away from us like rockets. Space itself is stretching, carrying them along for the ride. This is a subtle but crucial distinction, and it's one that even a lot of science communicators get wrong. When you see those animations of the Big Bang, the ones that show a little dot exploding outward in a burst of light and color, that's misleading. It makes it look like the Big Bang was an explosion in space, but it wasn't. It was an explosion of space. Space-time itself came into being and immediately started expanding, cooling as it did so, eventually allowing matter and energy to condense out of the primordial soup into the atoms and molecules and stars and galaxies we see today. Now, you might be wondering, if the universe is expanding, what's it expanding into? And that's another one of those questions that sounds perfectly reasonable, but doesn't quite work the way you think it does. The answer is, it's not expanding into anything. There is no outside. The universe isn't a balloon inflating into a room. The balloon analogy is useful for visualizing how space expands, how points on the surface of the balloon get farther apart as you blow it up. But the analogy breaks down when you ask what's outside the balloon. In the case of the universe, there is no outside. The universe is all there is. Space only exists within the universe. Beyond the universe, there's no space to expand into. There's not even a beyond in any meaningful sense. I know this is frustrating. It's frustrating to me too, and I've been reading about this stuff for years. Our brains evolved to deal with medium-sized objects moving at medium speeds in a world where cause and effect are nice and linear. We did not evolve to intuitively understand the origin of space-time itself. So the fact that this is hard to wrap your head around, That's not a bug, it's a feature. It means you're actually engaging with the material and not just nodding along. So let's recap, because I know I've thrown a lot at you already. The Big Bang was not an explosion in space. It was the origin of space, time, matter, and energy. Before the Big Bang, and again that word before is doing a lot of questionable work here, there was no space, no time, and therefore no meaningful way to talk about what existed. The universe began as a singularity, a point of infinite density and temperature. And from that singularity, space-time began expanding and cooling. Now here's where things get even weirder, if you can believe that. Because as much as we've learned about the Big Bang over the past century, there's still this massive question mark sitting at the very beginning. The singularity itself is a problem. It's not just that our equations break down there, it's that the singularity might not even be a real physical thing. It might just be a sign that our theories are incomplete, that we're missing some crucial piece of the puzzle. Think about it this way. When you have a theory that predicts infinities showing up in physical reality, that's usually a red flag. Infinities tend to be mathematical artifacts, not actual properties of the universe. It's like if your GPS told you that your destination was infinitely far away. You wouldn't assume that your destination actually is infinitely far away. You'd assume there's a bug in the GPS software. In the same way, a lot of physicists suspect that the singularity is a sign that general relativity is breaking down at the extreme conditions of the early universe, and that we need a better theory to describe what was really going on. This is where quantum mechanics might come to the rescue. At the incredibly tiny scales and incredibly high energies present at the moment of the Big Bang, quantum effects should have been dominant. And one of the weird things about quantum mechanics is that it doesn't allow for true infinities in quite the same way. Quantum mechanics is all about probabilities and uncertainties. There's this principle called the Heisenberg uncertainty principle, which says that you can never know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This uncertainty is baked into the fabric of reality at the quantum level. If we apply quantum mechanics to the very early universe, it suggests that maybe the singularity wasn't actually infinitely small and infinitely dense. Maybe there was some minimum size, some tiny but non-zero volume within which all the energy of the universe was contained. This would get rid of the troublesome infinities and give us a more physically plausible picture of the beginning. But to really figure this out, we need that elusive theory of quantum gravity, the one that nobody's quite managed to nail down yet. Now, here's the part where I have to level with you. Everything I've just described, all this talk about singularities and space-time and quantum mechanics, that's all based on our best current understanding of physics. And our best current understanding is very, very good. It's supported by mountains of experimental evidence. We can trace the history of the universe back to fractions of a second after the Big Bang with remarkable confidence. We know what the temperature was, what kinds of particles existed, how they interacted. We've tested these predictions with particle accelerators like the Large Hadron Collider, which can recreate the conditions of the early universe in miniature. We've observed the afterglow of the Big Bang, the cosmic microwave background radiation, which fills the entire sky and tells us an enormous amount about the universe's infancy. But when we get right down to the moment of the Big Bang itself, to time equals 0, we're extrapolating. We're taking our theories and pushing them to their absolute limits and beyond. And we know that at some point, probably right around the Planck time, which is about 10 to the negative 43 seconds after the Big Bang, our current theories stop being reliable. The Planck time is the smallest meaningful unit of time in physics. Below that scale, The quantum fluctuations in space-time itself become so large that our classical notions of space and time break down completely. So when I talk about what happened at time equals zero, at the singularity, you have to understand that's speculation. Educated speculation based on solid physics, but speculation nonetheless. And this brings us back to the question of nothing. Because if we can't reliably describe what happened at the moment of the Big Bang, if our theories break down right when things get really interesting, then how can we possibly talk about what came before? How can we discuss the state of nothing that supposedly preceded everything? Well, the honest answer is we can't. Not with certainty. But that doesn't mean we can't make informed guesses. That doesn't mean we can't use the tools of physics and mathematics to explore possibilities, to construct models, to see where the logic leads us. And that's exactly what physicists have been doing for decades. They've been chipping away at this problem from every conceivable angle, using every trick in the book, and they've come up with some genuinely wild ideas about what nothing might have looked like, and whether before the Big Bang is even a coherent concept. Some of these ideas suggest that there was something before the Big Bang, some pre-existing state that gave rise to our universe. Some suggest that the universe is cyclical, that Big Bangs happen over and over again in an eternal cosmic rhythm. Some suggest that our universe is just one bubble in an infinite froth of universes, each with its own Big Bang, its own laws of physics, its own story. And some suggest that the question itself is misguided, that the universe is self-contained, that it created itself in a kind of cosmic bootstrap paradox that makes time travel movies look straightforward by comparison. We're going to explore all of these ideas in the chapters ahead. We're going to dive deep into the physics of the very early universe, into the evidence that supports our current models, and into the speculative frontiers where science blurs into philosophy. But before we do that, I wanted to make sure we had a solid foundation. I wanted to make sure you understood why the question, what was there before the Big Bang, is so tricky. Why our everyday intuitions fail us so completely when we try to think about cosmic origins. Because here's the thing, the universe doesn't owe us an explanation that makes intuitive sense. Reality is under no obligation to conform to our expectations. The universe is what it is, and our job as curious humans is to observe it, measure it, test our ideas against it, and slowly, painstakingly build up a picture of how it works. And sometimes that picture is going to be weird. Sometimes it's going to violate our common sense. Sometimes it's going to involve concepts like space-time coming into existence, or there is no before, that make our brains want to short-circuit. But that's okay. That's part of the journey. And honestly, it's part of the fun. Because if the universe was simple and straightforward and easily comprehensible, if we could figure it all out just by sitting in our armchairs and thinking real hard, it would be boring. The fact that reality is strange and surprising and occasionally makes us feel like complete idiots, that's what makes it worth studying. So buckle up, because we're just getting started. We've established that nothing isn't what you think it is, that the Big Bang wasn't an explosion in space, but the origin of space itself, and that asking what came before runs into some serious conceptual roadblocks. But there's so much more to the story, because it turns out that the Big Bang, as we commonly understand it, might not actually be the beginning. There might have been something before that hot, dense state we call the Big Bang. Something cold and empty and strange. And understanding what that something was and how it gave rise to everything we see around us, That's going to require us to dive into some of the most cutting-edge physics of the last 50 years. We're going to talk about cosmic inflation, about quantum fields and vacuum energy, about how the universe went from nothing, or something very close to nothing, to everything. And trust me, it's going to get wild. The universe's first breath, inflation, and the primordial soup. Your brain hurts, my brain hurts, everyone's brain hurts. But here's where things get interesting, because we're about to talk about what happened immediately after the Big Bang. And I mean immediately. We're talking about timescales so short that blinking would take you through billions upon billions of these moments. We're talking about the universe's first breath, the moment when everything went from impossibly small to still incredibly small, but significantly less impossibly small. And this moment, this fraction of a second, shaped literally everything we see in the universe today. So let's rewind the clock. 13.8 billion years ago, the universe begins. Space-time springs into existence, and it's hot, like really hot. When I say the early universe was hot, I'm not talking about the surface of the sun hot, or even the core of the sun hot. I'm talking about temperatures that make stellar fusion look like an ice bath. In the very first trillionth of a second after the Big Bang, we're looking at temperatures exceeding 10 to the 32 degrees Kelvin. That's 10 with 32 zeros after it. For reference, the core of the sun is about 15 million degrees Kelvin. The Large Hadron Collider can create temperatures of around 5 trillion degrees when smashing particles together, which sounds impressive until you realize that's still about 1 billion trillion times cooler than the universe at 10 to the negative 43 seconds old. At these temperatures, matter as we know it couldn't exist. Atoms couldn't form. Hell, even protons and neutrons couldn't form. The universe was so hot and so energetic that individual particles were being created and destroyed constantly in a chaotic soup of pure energy. This is what physicists call the quark-gluon plasma, a state of matter where quarks, the fundamental building blocks of protons and neutrons, float around freely instead of being bound together. It's the most extreme state of matter we know of, and in the early universe, that's all there was. Now, as the universe expanded, it cooled. That's just basic thermodynamics. When you expand a gas, it cools down. Same principle applies to the universe itself. Space-time was expanding, stretching, and as it did, the temperature dropped. But here's the thing. According to our standard models of cosmology, this expansion should have been smooth and steady. The universe should have gradually cooled as it grew, eventually reaching temperatures low enough for particles to stick together, for atoms to form, for stars and galaxies to emerge billions of years down the line. But when physicists started really digging into the details of this picture in the 1970s and early 80s, they noticed some problems, big problems. Problems that threaten to unravel our entire understanding of the Big Bang. And these problems were so significant that they required a completely new idea, something radical and unexpected to solve them. That idea was cosmic inflation, and it fundamentally changed how we think about the early universe. Let me explain the problems first, because you need to understand what was broken before you can appreciate how inflation fixed it. The first major issue was called the horizon problem. Here's the deal. When we look out into space in different directions, like say we look at the cosmic microwave background radiation, which is the afterglow of the Big Bang that fills the entire sky, we see that it's remarkably uniform. No matter which direction you look, the temperature is the same to within about 1 part in 100,000. That's incredibly uniform, like suspiciously uniform. Why is this a problem? Because according to the standard Big Bang model, without inflation, Different regions of the universe that we can see today should never have been in contact with each other. They should never have had a chance to exchange energy or information because they're too far apart, and the universe hasn't been around long enough for light to travel between them. In physics, we call the maximum distance that light could have traveled the horizon. If two regions are outside each other's horizon, they're causally disconnected. They can't influence each other because no signal, no information, not even light has had time to travel between them. So if these regions were never in contact, why do they have the same temperature? It's like if you had two pots of water on opposite sides of the planet and you measured them and found out they were both exactly 98.6 degrees. You'd be suspicious, right? You'd wonder how they ended up at the same temperature when they've never been in contact. That's the horizon problem. The universe is way too uniform given how disconnected different parts of it should be. The second problem was the flatness problem. Now, when cosmologists talk about the universe being flat, they're not saying it's two-dimensional like a sheet of paper. They're talking about the curvature of space itself. General relativity tells us that space can be curved by the presence of matter and energy. You can have positively curved space, like the surface of a sphere, where parallel lines eventually converge. You can have negatively curved space, like a saddle, where parallel lines diverge. Or you can have flat space, where parallel lines stay parallel forever, just like in the geometry you learned in high school. When we measure the curvature of our universe on large scales, we find that it's flat, or at least so close to flat that we can't measure any deviation. Now here's the weird part. For the universe to be flat today, it had to be extraordinarily flat in the early universe. Like fine-tuned to an absurd degree. If the density of the universe in the first second after the Big Bang had been off by even 1 part in 10 to the 60, the universe would have either collapsed back on itself almost immediately or expanded so fast that no structures could ever form. The fact that we're here, that galaxies exist, that you're sitting there reading or listening to this, means that the early universe had to have its density tuned to this incredible precision. And that seems really suspicious. It's like balancing a pencil perfectly on its tip and having it stay there for 13.8 billion years. Technically possible, but you'd be forgiven for thinking there's something else going on. These two problems, the horizon problem and the flatness problem, were major headaches for cosmologists. They suggested that either our models were incomplete or that the initial conditions of the Big Bang were fine-tuned in a way that seemed profoundly unlikely. And then in 1980, a physicist named Alan Guth had an idea that would solve both problems in one fell swoop. He proposed that in the very early universe, there was a brief period of extremely rapid expansion, far faster than the speed of light, that occurred before the more sedate expansion we observe today. He called this idea cosmic inflation. Here's how inflation works, at least in its simplest form. In the first tiny fraction of a second after the Big Bang, something like 10 to the negative 37 seconds, the universe was filled with a special kind of energy field called the inflaton field. Now, don't get too hung up on the name. The inflaton is a hypothetical field, meaning we've never directly detected it, but it's a useful concept for explaining what we observe. This inflaton field had a very special property. It created a kind of negative pressure, which sounds weird because we usually think of pressure as something that pushes outward, not inward. But this negative pressure acted like anti-gravity, causing space itself to expand exponentially fast. And when I say exponentially fast, I mean it. During inflation, the universe didn't just grow steadily. It doubled in size over and over again in incredibly short intervals. Estimates suggest that the universe doubled in size every 10 to the negative 37 seconds or so. That might not sound like much, but exponential growth is deceptive. It starts slow and then goes absolutely bananas. By the time inflation ended, somewhere between 10 to the negative 35 and 10 to the negative 33 seconds after the Big Bang, the universe had expanded by a factor of at least 10 to the 50th. Some models suggest even more, like 10 to the 78 or beyond. To put that in perspective, the universe went from being smaller than a proton to roughly the size of a softball in less time than it takes light to cross the nucleus of an atom. And in doing so, it grew by more in that fraction of a second than it has in the entire 13.8 billion years since. This is absolutely mind-blowing. During inflation, the expansion of space was faster than the speed of light. Now, before you get all excited and start thinking this violates Einstein's theory of relativity, hold on. Nothing was actually moving through space faster than light. That's still forbidden by relativity. What was happening is that space itself was expanding faster than light could cross it. There's no rule in physics that says space can't expand faster than light. In fact, space can expand at any speed it wants. The speed limit only applies to objects moving through space, not to space itself. So why does inflation solve the horizon problem? Because if the entire observable universe today started out as a tiny region, much smaller than a proton before inflation, then that tiny region would have been well within its own horizon. Everything in that region would have had time to reach the same temperature, to equilibrate, to smooth out any irregularities. Then inflation kicked in and blew that tiny smooth region up to an enormous size, far larger than the observable universe today. So when we look out and see the cosmic microwave background and notice that it's incredibly uniform, that's because it all came from a tiny patch that was already uniform before inflation stretched it out. Problem solved. And what about the flatness problem? Well, inflation solves that too, and in a really elegant way. Imagine you're standing on the surface of a balloon. If the balloon is small, you can easily see that the surface is curved. But now imagine inflating that balloon to the size of the Earth. If you're standing on the surface, it's going to look pretty flat to you locally because the curvature is spread out over such a huge area. Now imagine inflating it to the size of the solar system, or the galaxy, or the observable universe. At that point, any initial curvature is completely negligible. The surface looks flat for all practical purposes. That's what inflation does to space. It takes whatever curvature existed initially and stretches it out so much that the universe appears flat on the scales we can observe. It's like taking a wrinkled sheet and pulling it so tight that all the wrinkles disappear. But inflation doesn't just solve these problems. It also gives us a beautiful explanation for one of the biggest mysteries in cosmology. Where did all the structure in the universe come from? When we look out at the universe today, we see galaxies, clusters of galaxies, superclusters, enormous voids, a cosmic web of structure stretching across billions of light years. Where did all this come from? If the early universe was smooth and uniform, how did we end up with all this complexity? The answer lies in quantum mechanics, which, as we've discussed, is the physics of the very small. At the quantum level, nothing is ever perfectly smooth or perfectly still. There are always fluctuations, tiny random variations in energy and density, popping in and out of existence due to the Heisenberg uncertainty principle. Under normal circumstances, these quantum fluctuations are so small that they don't matter on macroscopic scales. They're confined to the microscopic realm of atoms and subatomic particles. But during inflation, something remarkable happened. These tiny quantum fluctuations were stretched out along with space itself. They were blown up from subatomic scales to cosmic scales. What started as microscopic variations in the inflaton field became macroscopic variations in the density of matter and energy across the universe. These variations weren't huge. They were only about 1 part in 100,000, but that was enough. In regions that were slightly denser than average, gravity pulled in more matter over time, making them even denser. In regions that were slightly less dense, matter drained away, making them even emptier. Over hundreds of millions of years, these tiny density variations grew into the galaxies and clusters and voids we see today. This is genuinely one of the most stunning ideas in all of cosmology. The structures we see in the universe today, the Milky Way galaxy, the Andromeda galaxy, the massive Virgo supercluster, all of it traces back to quantum fluctuations that occurred during a fraction of a second, 13.8 billion years ago. We are, quite literally, living in the echo of quantum noise that got amplified to cosmic proportions by inflation. That's not just poetic, that's actual physics, and it's supported by observations. When we look at the cosmic microwave background radiation, we can see these tiny variations in temperature, about 1 part in 100,000, and they match the predictions of inflation incredibly well. Now, let's talk about what the universe looked like after inflation ended, because that's where the story gets even more interesting. When inflation stopped, all that energy that was driving the expansion didn't just disappear, it had to go somewhere. This energy was stored in the inflaton field, and when inflation ended, the inflaton field decayed. Its energy was converted into particles, into matter and radiation. This process is called reheating, and it's what populated the universe with all the stuff we're familiar with. Reheating was violent and energetic. All the potential energy of the inflaton field got dumped into the universe in the form of particles and heat. The temperature skyrocketed. We're talking about temperatures around 10 to the 32 degrees Kelvin, maybe higher depending on the details of the model. The universe became an incredibly hot, incredibly dense soup of fundamental particles. Quarks, gluons, electrons, neutrinos, photons, all the basic building blocks of matter were created in this process, along with their antiparticles. This is what cosmologists call the quark-gluon plasma, or the primordial soup, the state of matter that existed in the first fractions of a second after inflation ended. In this primordial soup, particles and antiparticles were constantly being created and annihilating each other in flashes of energy. The density and temperature were so extreme that nothing stable could exist. It was pure chaos, a roiling maelstrom of energy and matter in equilibrium. But as the universe continued to expand, it cooled. And as it cooled, things started to settle down. By about 1 second after the Big Bang, the temperature had dropped to around 10 billion degrees Kelvin. That's still incredibly hot, about 18 billion degrees Fahrenheit, but it was cool enough for some important transitions to start happening. At this point, the universe was still too hot for atoms to form. Any atom that tried to come together would immediately be blasted apart by the intense radiation. But quarks could now bind together to form protons and neutrons, the building blocks of atomic nuclei. This process is called quark confinement, and it's one of the key milestones in the early universe. Before this, quarks floated around freely. After this, they were locked inside protons and neutrons, which is how we find them in the universe today. Over the next few minutes, the universe cooled enough for nuclear fusion to occur. protons and neutrons started sticking together to form the nuclei of light elements: hydrogen, helium, a tiny bit of lithium. This period is called Big Bang nucleosynthesis, and it lasted only a few minutes. But in that time, about 25% of the universe's mass was converted from hydrogen into helium. This is why the universe is roughly 3/4 hydrogen and 1/4 helium by mass today. Those proportions were set in the first few minutes after the Big Bang, and they're one of the key pieces of evidence supporting the Big Bang model. But even after nucleosynthesis, the universe was still way too hot for atoms to form. It was still a plasma, a soup of nuclei and free electrons, and it was opaque to light. Photons couldn't travel very far without scattering off free electrons. The universe was essentially a fog, glowing white-hot, but completely opaque. This state persisted for hundreds of thousands of years as the universe continued to expand and cool. Now, I want to take a step back and appreciate what we've just covered, because it's easy to get lost in the details and miss the bigger picture. In the span of less than a second, the universe went from a state of almost unimaginable density and temperature through a period of exponential expansion that dwarfs anything that's happened since, to a hot but gradually cooling primordial soup filled with the basic ingredients of matter. All of this happened before the universe was even a second old, and all of this set the stage for everything that came after: the formation of atoms, the birth of stars, the creation of galaxies, the emergence of planets, and eventually, improbably, you and me, sitting here trying to make sense of it all. But here's the thing. As successful as inflation is at solving the horizon problem and the flatness problem and explaining the origin of structure, it's still a hypothesis. We don't have direct evidence for inflation. We've never detected the inflaton field. We don't know exactly what it is or how it behaves. There are dozens of different models of inflation, each with slightly different predictions, and physicists are still trying to figure out which one, if any, is correct. Some critics argue that inflation isn't even necessary, that maybe there are other ways to solve the horizon and flatness problems that we haven't thought of yet. And some go even further, arguing that inflation actually makes the problem worse in certain ways, that it requires its own fine-tuning to get started in the first place. These debates are ongoing, and they're part of what makes cosmology so exciting. We're not just passively accepting a story handed down to us. We're actively testing it, refining it, looking for ways to prove or disprove it. And one of the key ways we test inflation is by looking for its fingerprints in the cosmic microwave background radiation, that faint glow of light left over from when the universe became transparent for the first time. That radiation, which fills the entire sky, is our best window into the early universe, and it's absolutely packed with information. It tells us about the temperature and density of the universe at different times, about the patterns of structure that were imprinted during inflation, about the overall composition and geometry of the cosmos. In fact, the cosmic microwave background is so important that it deserves its own deep dive. Because as much as inflation explains, the real proof is in the pudding, or in this case, in the faint microwave glow that surrounds us on all sides. That glow is the echo of creation, the afterimage of the Big Bang, and it's one of the most powerful tools we have for understanding where we came from and what happened in those first fractions of a second when the universe took its first breath. All right, so we've talked about how the universe burst into existence, how it went through this insane period of exponential growth called inflation, and how it then settled into a hot, dense soup of particles and radiation. But here's the thing. All of that, as mind-blowing as it is, would just be theoretical speculation if we didn't have actual evidence to back it up. And I'm not talking about evidence in the sense of, well, the math works out, so it's probably true. I'm talking about direct, observational, look up at the sky and see it yourself evidence. And that evidence exists. It's called the cosmic microwave background, or CMB for short, and it is hands down one of the most important discoveries in the history of science. It's our baby picture of the universe, a snapshot taken when the cosmos was just 380,000 years old, and it tells us more about where we came from than just about anything else we've ever found. Now, before we get into what the CMB actually is and why it's so incredible, I need to set the stage a little bit. We need to talk about what the universe was like in those first few 100,000 years after the Big Bang, because understanding that is crucial to understanding why the CMB exists in the first place and what it's showing us. So picture this. The universe is expanding and cooling. Inflation has ended. Reheating has pumped the universe full of particles. And now we're in this phase where the temperature is dropping, but it's still insanely hot. In the first few minutes, like we talked about, Big Bang nucleosynthesis happened. Protons and neutrons stuck together to form the nuclei of hydrogen and helium. About 75% hydrogen, 25% helium by mass, with just a tiny sprinkle of lithium thrown in for good measure. But here's the key thing. Even though you had these atomic nuclei floating around, you didn't have atoms yet. And that's a really important distinction. An atom, as you probably remember from high school chemistry, is a nucleus with electrons orbiting around it. Hydrogen is one proton with one electron. Helium is two protons, two neutrons, and two electrons. But in the early universe, it was way too hot for electrons to stick to nuclei. The radiation, the photons flying around everywhere, had so much energy that any time an electron tried to settle into orbit around a nucleus, it would immediately get knocked loose again by a high-energy photon. So what you had was this plasma, this hot ionized gas where nuclei and electrons were just floating around separately, not bound together into atoms. And this plasma had a very specific property that's going to be really important for our story. It was opaque. Light couldn't travel very far through it. Every time a photon tried to move through space, it would run into a free electron and scatter off in a different direction. It's kind of like trying to see through fog. The fog itself isn't solid, but light can't penetrate very far because it keeps bouncing off the tiny water droplets suspended in the air. The early universe was like that, except instead of water droplets, you had free electrons, and instead of fog, you had a glowing, white-hot plasma filling all of space. This state of affairs persisted for a long time, cosmically speaking. The universe kept expanding, kept cooling, but it was still too hot for atoms to form. And then, about 380,000 years after the Big Bang, something really important happened. The temperature dropped to around 3,000 degrees Kelvin, which is still incredibly hot, like 5 times hotter than the surface of the sun, but it was cool enough that electrons could finally stick to nuclei without getting immediately blasted off again. This moment is called recombination, which is kind of a weird name because it implies that the electrons and nuclei were combined before and are now recombining, but that's not actually the case. This was the first time they were combining. But physicists already had the term recombination from studying plasmas in laboratories, so the name stuck, even though it's technically inaccurate. When recombination happened, the universe went through a phase transition. It went from being a plasma of free electrons and nuclei to being a gas of neutral atoms. And this changed everything. Because once the electrons were bound up inside atoms, they couldn't scatter photons anymore, at least not nearly as effectively. The universe became transparent, almost overnight, cosmically speaking. Light that had been trapped, constantly bouncing off electrons, was suddenly free to travel through space unimpeded. The fog lifted. The universe went from opaque to transparent, and all those photons that had been trapped in the plasma, they just started traveling in straight lines. They've been traveling ever since, for the last 13.4 billion years, spreading out as the universe expanded, cooling down as their wavelengths got stretched by the expansion of space. And today, those photons are still here. They're all around us, coming from every direction in the sky, and we can detect them with radio antennas and microwave detectors. That's the cosmic microwave background. It's the light from the moment the universe became transparent, the echo of creation, the afterglow of the Big Bang. Now, let's talk about the discovery of the CMB, because it's honestly one of the best stories in the history of science, and it involves two guys who had absolutely no idea what they were looking at. The year was 1964, and two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey. They had this big radio antenna, originally built for satellite communications, and they wanted to use it to study radio signals from the Milky Way. But they had a problem. No matter what they did, they kept picking up this annoying background noise. It was a faint hiss, and it was coming from every direction in the sky. At first, they thought it was just interference from nearby New York City, or maybe pigeons nesting in the antenna. I'm not joking. There were actually pigeons living in the antenna, and Penzias and Wilson spent a considerable amount of time cleaning out pigeon droppings, what they diplomatically called a white dielectric material, to see if that was causing the noise. Spoiler alert, it wasn't. They cleaned the antenna, they checked all their equipment, they pointed the antenna in different directions, and the noise was always there. Same intensity, same frequency, coming from everywhere. Meanwhile, just a few miles away at Princeton University, a team of physicists led by Robert Dicke were building an experiment to try to detect the cosmic microwave background. See, back in 1948, two physicists named Ralph Alpher and Robert Herman had predicted that if the Big Bang really happened, there should be leftover radiation from the early universe, and it should have cooled down to a temperature of around 5 degrees Kelvin by now. 5 Kelvin is 5 degrees above absolute zero, which translates to about minus 450 degrees Fahrenheit. At that temperature, the radiation would be in the microwave part of the spectrum, hence the name, cosmic microwave background. But here's the thing. Alpher and Herman's prediction kind of got ignored for a couple of decades. It was in the literature, but not a lot of people were paying attention to it. The technology to detect such faint microwave radiation didn't really exist yet, and the Big Bang theory itself was still pretty controversial. There was a competing theory called the steady-state theory, which said that the universe didn't have a beginning, that it had always existed and was constantly creating new matter to maintain a constant density as it expanded. That theory was actually pretty popular in the 1950s and early 60s, and a lot of prominent astronomers believed it. So Dicke's team at Princeton were gearing up to try to detect this predicted radiation and prove once and for all that the Big Bang had happened. But before they could finish building their detector, Penzias and Wilson stumbled into the discovery completely by accident. When Penzias mentioned the mysterious noise to a colleague, word eventually got back to the Princeton team, and they realized immediately what Penzias and Wilson had found. It was the cosmic microwave background. It was the smoking gun, the definitive proof that the Big Bang had occurred. In 1965, both teams published their results in back-to-back papers in the Astrophysical Journal. Penzias and Wilson described the detection of the signal, and Dickey's team explained what it meant. And just like that, cosmology changed forever. The steady-state theory was dead. The Big Bang was real. The universe had a beginning, and we were looking at the light from that beginning. Penzias and Wilson later won the Nobel Prize in Physics in 1978 for their discovery, which, considering they were mostly just annoyed by pigeon poop, is a pretty good outcome. Now, let's talk about what the CMB actually tells us, because this isn't just some faint glow in the sky that confirms the Big Bang happened. The CMB is absolutely packed with information. It's like the universe's medical records, its birth certificate, its entire early history encoded in this faint microwave radiation. First off, the temperature. When Penzias and Wilson first detected it, they measured a temperature of about 3 degrees Kelvin. More precise measurements over the years have refined that number. Today, we know the CMB has a temperature of 2.72548 degrees Kelvin, give or take about 0.00057 degrees. That's minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. It's cold, really cold, just barely above the absolute coldest temperature possible in the universe. But here's the remarkable thing. That temperature is almost exactly the same everywhere you look in the sky. If you point a detector in one direction and measure the CMB temperature, then point it in the complete opposite direction and measure it again, the temperature is the same to within about 1 part in 100,000. That level of uniformity is incredible. It means that the universe, at least the part we can see, was incredibly smooth and homogeneous back when the CMB was emitted. And that uniformity is exactly what inflation predicts. Remember, inflation stretched out a tiny region of space that was already in thermal equilibrium, already at the same temperature everywhere. The CMB is the proof that inflation's prediction was correct. But here's where things get really interesting. While the CMB is incredibly uniform overall, it's not perfectly uniform. There are tiny variations in temperature, tiny hot spots and cold spots that deviate from the average by about 1 part in 100,000. These variations are called anisotropies, and they are the single most important feature of the CMB. Why? Because those anisotropies are the seeds of all the structure we see in the universe today. Let me explain. Remember how we talked about quantum fluctuations during inflation getting stretched out to cosmic scales? Those fluctuations created regions that were slightly denser than average and regions that were slightly less dense. In the denser regions, there was a little bit more matter, which meant a little bit more gravity, which meant those regions had a slightly higher temperature. In the less dense regions, there was a little bit less matter, a little bit less gravity, and a slightly lower temperature. These temperature differences were tiny, but they were there, and they got imprinted on the CMB at the moment of recombination. After recombination, those denser regions started pulling in more matter because they had more gravity. The rich got richer, cosmically speaking. Over millions and billions of years, those tiny overdensities grew into the galaxies and galaxy clusters we see today. The underdense regions became the voids, the vast empty spaces between galaxy clusters. So when we look at the anisotropies in the CMB, we're literally seeing the blueprints for the universe's large-scale structure. We're seeing the baby picture of galaxies before galaxies existed, just faint patterns of density variation in the primordial plasma. This is why cosmologists get so excited about measuring the CMB in ever greater detail.
In 1989, NASA launched a satellite called the Cosmic Background Explorer, COBE for short, which was specifically designed to study the CMB. COBE was a game changer. It confirmed that the CMB had a perfect black body spectrum, meaning it matched the theoretical predictions from quantum mechanics for radiation in thermal equilibrium.
The spectrum was so perfect, in fact, that it's the most precise black body ever measured in nature. When the COBE team presented their data at a scientific conference, the audience gave them a standing ovation. That doesn't happen often in physics. COBE also made the first detailed maps of the CMB anisotropies. The maps were pretty low resolution by modern standards, but they showed those tiny temperature fluctuations clearly for the first time. George Smoot, one of the lead scientists on COBE, famously said it was like seeing the face of God, which was a bit dramatic, but you get the idea. The team won the Nobel Prize in 2006. After COBE, there was a whole series of increasingly sophisticated experiments to map the CMB in greater detail. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP for short, which produced much higher resolution maps. And then in 2009, the European Space Agency launched Planck, which has given us the most detailed maps of the CMB to date. These maps are stunning. They show the temperature variations across the entire sky in exquisite detail, with each pixel representing a tiny patch of the universe as it was 380,000 years after the Big Bang.
And here's the crazy part. We can analyze these maps using sophisticated statistical techniques to extract an enormous amount of information. We can measure the average density of matter in the universe, the density of dark matter, the density of dark energy, the rate of expansion, the curvature of space, the age of the universe, all from this one source of data. The CMB is the gift that keeps on giving. For example, by studying the pattern of hot and cold spots in the CMB, we can determine that the universe is flat, at least to within a tiny margin of error. Remember the flatness problem we talked about earlier? The CMB confirms that inflation solved it.
The universe is so flat on large scales that we can't measure any curvature. We can also determine that ordinary matter, the stuff that makes up stars and planets and you and me, accounts for only about 5% of the total energy density of the universe. About 27% is dark matter, this mysterious, invisible stuff that doesn't interact with light but does exert gravitational pull. And the remaining 68% is dark energy, an even more mysterious force that's causing the expansion of the universe to accelerate. All of this comes from analyzing the CMB. We can also measure the age of the universe with remarkable precision. By looking at how the CMB has cooled over time and combining that with measurements of the expansion rate, we get an age of 13.797 billion years, plus or minus about 20 million years. That's an error bar of less than 0.1%. We know the age of the universe more precisely than we know the age of the Earth, which is pretty wild when you think about it. But the CMB isn't just telling us about the universe as a whole. It's also telling us about specific events and processes that happened along the way. For example, there's this effect called the Sunyaev-Zeldovich effect, named after the two Russian physicists who predicted it in 1969. When CMB photons pass through a cluster of galaxies, they can scatter off high-energy electrons in the hot gas that fills those clusters. This scattering shifts the photons to slightly higher energies, which shows up as a tiny distortion in the CMB spectrum in the direction of that cluster. By studying these distortions, we can learn about the properties of galaxy clusters, how they formed, how they evolved, even measure distances to them in ways that are independent of other methods. There's also the Sachs-Wolfe effect, named after Rainer Sachs and Arthur Wolfe, who described it in 1967. This effect relates to how photons gain or lose energy as they climb out of or fall into gravitational wells. Photons coming from over-dense regions have to work harder to escape the extra gravity, so they lose a bit of energy and appear slightly cooler. Photons coming from under-dense regions don't have to work as hard, so they appear slightly warmer. By studying the pattern of these temperature variations, we can map out the distribution of matter in the universe at the time of recombination and see how it relates to the distribution of matter today. Now, I'll be honest with you, measuring the CMB is not easy.
It's a faint signal to begin with, and there's a ton of stuff that can interfere with it. If you point a telescope at the sky and try to measure microwaves, you're going to pick up all kinds of noise. There's radiation from our own galaxy, synchrotron emission from electrons spiraling in magnetic fields, free emission from ionized gas, dust in the Milky Way glowing in the infrared and microwave, not to mention human-made interference from cell phone towers and satellites and microwave ovens. Sorting out the CMB signal from all this foreground junk is a major challenge, and it requires sophisticated data analysis and a lot of clever engineering. This is why most CMB experiments are done from space or from remote locations like Antarctica, where the atmosphere is thin and dry. Water vapor in the atmosphere absorbs microwaves, so you want to get above as much of it as possible. And you want to be as far away from human civilization as you can get to avoid radio interference. The Planck satellite, for example, orbited at a point in space about 1 million miles from Earth, where it could observe the CMB with minimal interference. There's also a challenge related to frequency. The CMB is brightest at a frequency of around 160 gigahertz, which is in the microwave part of the spectrum. But different sources of foreground contamination dominate at different frequencies. Below about 10 gigahertz, emission from our galaxy drowns out the CMB. Above about 200 gigahertz, dust emission becomes a problem. So most CMB experiments focus on the frequency range from about 30 to 200 gigahertz, where the CMB signal is strong and the foreground contamination is manageable. But even within that range, you have to carefully model and subtract out all the foreground sources to get a clean measurement of the CMB itself. And then there's the issue of our own motion.
The Earth is moving around the Sun. The Sun is moving around the galaxy is moving through the universe, and all of that motion creates a Doppler shift in the CMB. In one direction, the direction we're moving toward, the CMB appears slightly hotter because we're blue shifting it. In the opposite direction, it appears slightly cooler because we're red shifting it. This creates a dipole pattern in the CMB, a systematic variation from one side of the sky to the other that's about 1,000 times larger than the intrinsic anisotropies we actually care about. Fortunately, this dipole is easy to identify and subtract out, and in fact, it's been used to measure our motion through the universe. We're moving at about 370 kilometers per second relative to the CMB rest frame, which is a useful piece of information in its own right. So, despite all these challenges, scientists have managed to measure the CMB with incredible precision. The current maps from Planck are so detailed that we can see features as small as about 5 arc minutes across, which is about 1/6 the diameter of the full moon. And the data from these maps has been used to test and refine our models of the universe to an extent that would have seemed like science fiction just a few decades ago. But here's the thing, and this is something I want to emphasize because it's easy to get lost in all the technical details and lose sight of the bigger picture. The CMB is not just a data set. It's not just numbers and graphs and temperature maps. It's a window into the past,
a direct connection to a time when the universe was unimaginably different from what it is today. When we look at the CMB, we're seeing light that has been traveling through space for 13.4 billion years.
That light was emitted by a universe that was 1,000 times smaller and 1,000 times hotter than it is now. A universe with no stars, no galaxies, no planets, no life, just a vast ocean of hydrogen and helium cooling in the darkness. And yet, encoded in that light is the story of everything that came after. The seeds of galaxies are there. The parameters that determine the universe's fate are there. The evidence for dark matter and dark energy is there. It's all there if you know how to look. The CMB is proof that the universe had a beginning, that it evolved according to physical laws we can understand, that the story we've been telling about inflation and nucleosynthesis and recombination isn't just speculation. It's backed up by hard evidence, by observations anyone can make if they have the right equipment. And I think that's what makes the CMB so profoundly important. It's not just that it confirms the Big Bang Theory, although that's certainly a big deal. It's that it gives us a way to study the universe when it was young, to see it in a state that no longer exists, to answer questions about its origin and composition and evolution that would otherwise be completely inaccessible. We can't travel back in time, but the CMB is the next best thing. It's a message from the past, written in light, waiting for us to decode it. Now, as incredible as all of this is, we're not done yet. Because while the CMB tells us a lot about the universe when it was 380,000 years old, it doesn't tell us everything. There are still big questions left unanswered. What happened before recombination? What happened during inflation? What was going on at the very instant of the Big Bang, at time zero, when our equations break down and the singularity rears its head? To answer those questions, we need to go deeper. We need to dive into the quantum realm, into the world of virtual particles and vacuum fluctuations, and the bizarre, counterintuitive rules that govern the smallest scales of reality. Because it turns out that nothing, in the quantum sense, isn't really nothing at all. And understanding what quantum nothing actually is might just hold the key to understanding where the universe came from in the first place. The quantum abyss, when nothing isn't empty. All right, so we've established that the cosmic microwave background is essentially the universe's baby picture, a snapshot of what things looked like when the cosmos was just 380,000 years old. We've seen how that faint microwave glow tells us about the temperature, the density, the composition of the early universe, and how tiny variations in that glow became the seeds for all the structure we see today. But here's where things get really weird. And I mean genuinely, mind-bendingly weird, in a way that makes everything we've talked about so far look positively straightforward by comparison. Because we need to talk about what happened before the CMB was emitted, before recombination, before nucleosynthesis, before inflation even. We need to talk about the quantum realm, about the nature of empty space itself, and about why the entire concept of nothing breaks down completely when you apply the rules of quantum mechanics. Now, I know what you're thinking. Quantum mechanics. Great. Here we go with the Schrodinger's cat and the particles being in two places at once and all that stuff that sounds like it was made up by someone who ate too many mushrooms. And look, I get it. Quantum mechanics has this reputation for being incomprehensible, for being so weird and counterintuitive that even the people who work with it every day don't really understand it. There's a famous quote, probably apocryphal, but still great, where Richard Feynman supposedly said, If you think you understand quantum mechanics, you don't understand quantum mechanics. Or his actual quote, which is equally telling, "Shut up and calculate." Basically, stop trying to make intuitive sense of it and just use the math, because the math works even if your brain doesn't want to accept what it's telling you. But here's the thing. We need to understand at least the basics of quantum mechanics if we're going to make any headway on this question of what existed before the Big Bang. Because quantum mechanics completely rewrites the rules about what nothing even means. In the classical physics world, the world of Newton and everyday experience, empty space is just that, empty. It's a void, a vacuum, a region of space where there's no matter and no energy. Remove all the particles, remove all the radiation, and you're left with nothing. Simple. But quantum mechanics says not so fast. Quantum mechanics says that even if you remove every single particle, every single bit of radiation, every single thing you can possibly remove from a region of space, you still don't have nothing. You have something. You have a seething, bubbling, frothing cauldron of activity at scales so small and timescales so short that they're completely invisible to us. But they're there, and they're real, and they have measurable effects on the universe. This is what physicists call the quantum vacuum, and it is one of the strangest and most profound concepts in all of physics. So let's start with the basics. What is quantum mechanics? At its core, quantum mechanics is the set of rules that govern the behavior of matter and energy at the smallest scales. We're talking about atoms, subatomic particles, photons, the fundamental building blocks of reality. And the key insight of quantum mechanics, the thing that makes it so different from classical physics, is that at these scales, things don't behave like little billiard balls following predictable trajectories. Instead, they behave like waves, or sometimes like particles, or sometimes like both at the same time. It depends on how you're measuring them, which is itself deeply weird. One of the foundational principles of quantum mechanics is something called the Heisenberg uncertainty principle, named after Werner Heisenberg, who formulated it in 1927. Now, the uncertainty principle is often misunderstood. People hear uncertainty and they think it means we just don't have good enough measuring equipment, that if we built more precise instruments, we could nail down exactly what's going on. But that's not it at all. The uncertainty principle is a fundamental limit on what can be known, a statement about the nature of reality itself, not about the limitations of our tools. The most famous version of the uncertainty principle says that you cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you measure where a particle is, the less precisely you can know how fast it's moving and in what direction, and vice versa. If you nail down the momentum with high precision, the position becomes fuzzy. This isn't a bug, it's a feature. It's baked into the fabric of quantum reality. But there's another version of the uncertainty principle that's even more important for our story, and it relates to energy and time. The energy-time uncertainty principle says that the uncertainty in energy multiplied by the uncertainty in time has to be greater than or equal to a very small number called h-bar divided by 2. H-bar is the reduced Planck constant, a fundamental constant of nature that shows up all over quantum mechanics, and it has a value of about 1.05 times 10 to the negative 34 joule seconds. That's an absurdly small number, which is why quantum effects don't show up in everyday life. But at the smallest scales, this number is everything. What the energy-time uncertainty principle tells us is this. If you look at a very short interval of time, the uncertainty in energy can be very large. In other words, for brief moments, the universe is allowed to violate energy conservation. Energy can just appear out of nowhere as long as it disappears again quickly enough. The shorter the time interval, the larger the energy fluctuation that's allowed. And this isn't just theoretical speculation. This actually happens. It's happening right now, all around you, in every cubic centimeter of empty space. The vacuum is constantly fluctuating, borrowing energy from nowhere, creating particles and antiparticles out of nothing, and then having those particles annihilate each other a fraction of a second later, paying back the borrowed energy and leaving no trace that they were ever there. These temporary particles are called virtual particles, and they are absolutely crucial to understanding the quantum vacuum. Now, the word virtual makes them sound kind of fake, like they're not really real. And in a sense, that's true. They exist for such a short time that you can never directly observe them. They're gone before you can measure them. But even though they're virtual, they have real, measurable effects on the universe. They contribute to the interactions between other particles. They affect the properties of atoms. They even create a measurable force between metal plates in a vacuum, which is one of the coolest experimental confirmations of quantum mechanics that exists. Let me tell you about that experiment, because it's genuinely fascinating, and it proves beyond any doubt that the quantum vacuum is real. It's called the Casimir effect, named after Hendrik Casimir, who predicted it in 1948. Here's the setup. You take two perfectly flat, uncharged metal plates, and you place them very close together in a vacuum, like 10 nanometers apart, which is about 100 atoms wide. Classical physics says nothing should happen. The plates are uncharged, so there's no electromagnetic force between them. There's no air pushing them together or apart. They should just sit there, indifferent to each other's presence. But that's not what happens. The plates attract each other. There's a tiny but measurable force pulling them together, and that force gets stronger the closer you bring them. Why? Because of virtual particles. In the empty space between the plates, virtual particles are constantly popping into and out of existence. But because the plates are so close together, only certain wavelengths of virtual particles can fit in the gap. It's like a standing wave on a guitar string. Only certain frequencies can exist. But outside the plates, in the vast expanse of empty space, all wavelengths are allowed. So there are more virtual particles pushing on the outside of the plates than pushing on the inside, and this creates a net force pushing the plates together. This effect was first measured experimentally in 1997 by Steve Lamoureux, and the results matched the theoretical predictions to within 5%. Since then, the experiment has been replicated with greater precision, and the agreement with theory is even better. The Casimir effect is proof that the quantum vacuum is real, that virtual particles are real in the sense that they have real effects, and that empty space is anything but empty. Now, let's take this idea and run with it. If the vacuum is full of virtual particles popping in and out of existence, then it must have energy. Even in the so-called ground state, the lowest energy state possible, there's still this irreducible quantum jitter, this background hum of activity. Physicists call this zero-point energy because it's the energy of a system at zero temperature, at absolute zero, when classically, everything should be perfectly still. But quantum mechanically, nothing can ever be perfectly still because of the uncertainty principle. There's always some residual motion, some residual energy, even in the absolute ground state. If you add up the zero-point energy of all the quantum fields in the universe, you get a number. And that number is huge. Like stupidly huge.
Depending on how you do the calculation, you can get an energy density for the vacuum that's 10 to the 120th times larger than what we actually observe. This is called the cosmological constant problem, and it is one of the biggest unsolved problems in theoretical physics. We know the vacuum has energy. We can measure it through effects like the Casimir effect and through the accelerating expansion of the universe, which is driven by something called dark energy that looks suspiciously like vacuum energy. But the amount of vacuum energy we calculate from quantum mechanics is 120 orders of magnitude larger than the amount we measure.
That's not a small discrepancy. That's a universe-destroying, theory-breaking, everything we thought we knew is wrong level of discrepancy. Nobody knows how to resolve this. There are ideas. Maybe different contributions to the vacuum energy cancel out in some clever way that we haven't figured out yet. Maybe there's some symmetry in nature that forces the vacuum energy to be much smaller than the naive calculation suggests. Maybe our entire approach to quantum field theory is wrong at some fundamental level. But right now, it's a mystery. And it's a mystery that directly relates to the question of what existed before the Big Bang. Because vacuum energy, whatever its actual value is, might be exactly the thing that drove inflation. Let's connect the dots here. Inflation, as we talked about in the last chapter, was this period of exponential expansion in the first fraction of a second after the Big Bang. The universe doubled in size over and over again, growing by an enormous factor in an incredibly short time. And what drove this expansion? A field called the inflaton field that had negative pressure and acted like anti-gravity. But what is the inflaton field, really? One possibility is that it's just a fancy name for the vacuum energy of some quantum field, a field that for a brief moment was stuck in a high energy state before decaying down to a lower energy state, releasing all that stored energy and reheating the universe. In this picture, the quantum vacuum played a starring role in the birth of the universe. Before inflation, the universe might have been a tiny region of space, far smaller than an atom, sitting there in this false vacuum state, this high-energy but metastable state. And then, through a quantum fluctuation, a random jitter allowed by the uncertainty principle, that false vacuum started to decay. The decay released energy, which drove the expansion, which stretched space, which created more volume, which allowed more vacuum energy to drive more expansion, and the whole thing ran away in a self-feeding cycle until the inflaton field finally settled into its true ground state, and inflation ended. This is a genuinely plausible scenario for how the universe began, and it's grounded in real physics. False vacuum decay is a thing that can happen. Sidney Coleman worked out the mathematics of it back in 1977. It's like a ball sitting at the top of a hill. The top of the hill is a false vacuum, a metastable state. The ball could sit there for a long time, even forever if nothing disturbs it. But quantum mechanics says there's always a chance, however small, that the ball can tunnel through the hill to the valley below, the true vacuum, releasing energy in the process. And once that tunneling starts in one spot, it spreads at the speed of light, converting the false vacuum to the true vacuum as it goes. If this is what happened at the beginning of the universe, then the Big Bang wasn't really the beginning. The universe existed before the Big Bang, but it was in this weird, cold, empty state, sitting in a false vacuum, until a quantum fluctuation triggered inflation, and everything took off from there. This is a radically different picture from the traditional singularity story, and it's one that a lot of physicists find appealing because it gets rid of the problematic infinities. There's no need for a singularity if the universe started as a small but finite region of space that then inflated.
The Big Bang becomes a phase transition, not an origin point. But wait, there's more. Because the quantum vacuum isn't just about virtual particles and zero-point energy. At the absolute smallest scales, at distances smaller than the Planck length, which is about 10 to the negative 35 meters, space-time itself becomes fuzzy and uncertain.
The smooth fabric of space-time that we experience at macroscopic scales breaks down into this seething, chaotic mess that physicists call quantum foam. John Wheeler coined the term back in the 1950s, and it's a beautiful image. Space-time at the Planck scale isn't a smooth sheet. It's a foam, a froth, a constantly shifting landscape of tiny wormholes and quantum fluctuations where the usual rules of geometry don't apply. At these scales, the distinction between space and time breaks down. The concepts of before and after, here and there, become meaningless. Cause and effect get fuzzy. It's a realm where general relativity and quantum mechanics crash into each other head-on, and neither theory knows what to do. This is why physicists are so desperate to develop a theory of quantum gravity, something that can describe what's happening at the Planck scale in a consistent way. String theory is one attempt, loop quantum gravity is another. But we don't have a complete theory yet, and until we do, we're basically flying blind when we try to talk about what happened at the very beginning, at the Planck time, which is about 10 to the negative 43 seconds after the Big Bang. But here's the thing. Even though we don't have a complete theory of quantum gravity, we can still make educated guesses about what the quantum foam implies for the origin of the universe. Some models suggest that the Big Bang emerged from the quantum foam, that a random fluctuation in the foam, one of countless fluctuations happening all the time, just happened to grow large enough and persist long enough to trigger inflation and become a universe. In this picture, universes are being born all the time out of the quantum foam. Most of them collapse back down immediately, living for only a Planck time before disappearing. But every once in a while, one of them makes it, inflates, and becomes a full-fledged universe like ours. We're the lucky ones, the ones that didn't immediately collapse, and there could be countless other universes out there that we'll never see or interact with because they're causally disconnected from us. This is obviously speculative, and I want to be clear about that. We're not talking about established science here. We're talking about ideas at the frontier, hypotheses that are informed by our best current theories, but that go beyond what we can directly test with experiments or observations. But these ideas are worth taking seriously because they're grounded in real physics. Virtual particles are real. Zero-point energy is real. The uncertainty principle is real. The quantum foam might be real. And if all of these things are real, then they have implications for where the universe came from and what existed before the Big Bang. Now, I want to address something that might be bothering you at this point, because it bothers a lot of people when they first encounter these ideas. If particles can just pop into existence out of the vacuum, doesn't that violate the law of conservation of energy? Isn't energy supposed to be conserved? Isn't that like one of the fundamental rules of physics? And the answer is yes. Energy is conserved, but the uncertainty principle gives you a loophole. As long as the energy borrowed from the vacuum is paid back quickly enough, within the time allowed by the uncertainty principle, there's no violation. The universe is essentially getting a very short-term loan from the quantum bank, and as long as it pays it back before the loan officer notices, everything's fine. But here's where things get even weirder. In an expanding universe, the rules change a little bit. When space itself is expanding,
energy conservation becomes a more subtle concept.
General relativity tells us that energy isn't strictly conserved in an expanding universe because the expansion of space itself can create or destroy energy. During inflation, the universe was expanding so fast that the quantum fluctuations, these temporary virtual particles, got stretched out before they could annihilate. They were frozen in place, turned from virtual particles into real particles, and their energy was essentially stolen from the vacuum and turned into the matter and radiation that fills the universe today. This is one of the most profound ideas in modern cosmology. All the matter in the universe, all the stars and galaxies and planets and people, might have originated as quantum fluctuations in the vacuum. Fluctuations that got stretched out by inflation and turned into real stuff. The entire universe might be, in a very real sense, the ultimate free lunch. The energy came from the vacuum, was amplified by inflation, and never had to be paid back because the expansion of space broke the usual rules of energy conservation. You quite literally got something from nothing. Or at least from the quantum vacuum, which is the closest thing to nothing that actually exists in nature. Now, if your brain is hurting at this point, that's completely normal. This stuff is hard. It's hard for me, it's hard for professional physicists, it's hard for everyone. The quantum vacuum is one of those concepts that sounds simple when you first hear about it. Empty space has energy. Okay, cool. But the more you dig into it, the weirder and more counterintuitive it gets. And the implications for the origin of the universe are genuinely profound. If the vacuum is full of energy, if virtual particles are constantly appearing and disappearing, if space-time itself is a quantum foam at the smallest scales, then the whole concept of nothing goes out the window. There's no such thing as true nothingness in quantum mechanics. Even the most perfect vacuum you can imagine, devoid of all particles and radiation, is still buzzing with quantum activity. This raises a question, and it's a question that philosophers and physicists have been arguing about for years. If the quantum vacuum isn't really nothing, then what is it? Is it something? If so, where did it come from? Did it always exist, or was there some even more fundamental state that gave rise to the quantum vacuum? And if there was something even more fundamental, what was that? You can see how this quickly turns into an infinite regress, a chain of "but where did that come from?" questions that never ends. Some physicists argue that the quantum vacuum is the most fundamental thing there is, that it's not something that needs an explanation, because it's just the way reality works at the deepest level. The laws of quantum mechanics are the laws of the universe, and they imply the existence of the quantum vacuum, so that's just what you get. It's like asking why the universe has 3 dimensions of space instead of 4 or 17. It just does. That's the universe we live in. Other physicists argue that there must be something deeper, some more fundamental layer of reality that explains why the quantum vacuum has the properties it does. But we don't know what that layer would be, or if it even exists. And then there's the issue of the cosmological constant problem that I mentioned earlier, this huge discrepancy between the vacuum energy we calculate and the vacuum energy we measure. Some physicists think that solving this problem will require a complete rethinking of quantum mechanics, or general relativity, or both. Maybe our entire framework is wrong, and we need something radically new to make sense of what's going on. Others think it's just a calculation error, that we're missing some crucial piece of physics that will make everything click into place once we find it. But right now, more than 70 years after the Casimir effect was predicted, we still don't have a good answer. But let's bring this back to the Big Bang. The quantum vacuum, with all its weirdness and uncertainty and virtual particles, gives us a way to think about the origin of the universe that doesn't require a singularity. Instead of everything being compressed into an infinitely small point, you start with a tiny region of space, maybe Planck-sized, sitting in a high-energy vacuum state. A quantum fluctuation triggers inflation. The universe expands exponentially. The vacuum energy gets converted into matter and radiation. And you end up with the hot, dense state that we call the Big Bang. In this picture, the Big Bang isn't the beginning. It's the end of inflation and the start of the more familiar universe, governed by gravity and expansion and structure formation. This is an elegant idea, and it has a lot going for it. It solves the singularity problem, or at least sidesteps it. It explains where inflation came from. It gives a mechanism for creating all the matter and energy in the universe out of the quantum vacuum. And it's consistent with everything we know about quantum mechanics and general relativity, at least in the regimes where those theories are well tested.
But it also raises new questions, questions that we can't yet answer. What determined the properties of that initial vacuum state? Why did it decay when it did? Was there anything before the vacuum state, or is this just as far back as we can go? And here's the really frustrating part. We might never be able to answer these questions, at least not with experiments or observations. The Planck scale is so incredibly small, and the Planck time is so incredibly short, that we may never have the technology to probe those regimes directly.
The energies required to test quantum gravity are about 1 trillion times higher than what the Large Hadron Collider can achieve, and building a particle accelerator powerful enough to reach those energies would require more resources than exist on Earth. So we're stuck doing what physicists call Gedenken experiments, thought experiments, using the tools of mathematics and logic to explore possibilities and see where they lead. But even if we can't test these ideas directly, we can look for indirect evidence. We can study the cosmic microwave background in ever greater detail, looking for subtle signatures that might tell us about inflation and the quantum vacuum. We can search for gravitational waves from the early universe, ripples in space-time that might carry information about the first moments after the Big Bang. We can build more powerful telescopes and detectors and see if the patterns we observe in the universe match the predictions of our models. And slowly, piece by piece, we can build up a picture of what happened, even if we can never observe it directly. So where does this leave us? We've established that the quantum vacuum is not nothing. It's a seething, bubbling foam of virtual particles and quantum fluctuations and zero-point energy. It's the closest thing to nothing that exists in nature, but it's still something. And that something might be exactly what gave rise to the universe, or at least to the hot, dense state we call the Big Bang. The quantum vacuum is weird. It's counterintuitive. It challenges our everyday notions of reality. But it's real, and it's supported by experiments and observations that anyone can verify. But this still leaves us with a deeper question, one that takes us out of the realm of physics and into the realm of philosophy. If the quantum vacuum existed before the Big Bang, can we even talk about before in any meaningful sense? Time, as we understand it, is part of the structure of space-time, and space-time came into existence at the Big Bang, or at least took on its current form then. So what does it mean to ask what happened before time existed? Is that question even coherent? Or is it like asking, what's north of the North Pole? A question that sounds reasonable, but actually doesn't make sense when you think about it carefully. That's the philosophical paradox we need to wrestle with next, because understanding the limits of our questions is just as important as finding the answers.
The philosopher's paradox, asking before the Big Bang. All right, so we've just spent the last chapter diving deep into the quantum vacuum, this bizarre realm where nothing isn't actually nothing, where virtual particles pop in and out of existence like the universe is playing the most complicated game of whack-a-mole ever invented, and where the very fabric of space-time turns into a frothy, chaotic mess at the smallest scales. We've established that empty space is full of energy, that the uncertainty principle allows particles to borrow energy from nowhere as long as they pay it back fast enough, and that all of this quantum weirdness might be exactly what gave birth to the universe. But now we need to tackle what is probably the most fundamental question of all, the one that every single person asks when they hear about the Big Bang for the first time. What happened before the Big Bang? What was there before everything began? And this is where things get not just scientifically complicated, but philosophically uncomfortable. Because the answer, according to our best understanding of physics, is that the question itself might not even make sense. I know, that sounds like a cop-out. It sounds like physicists are just dodging the question because they don't have a good answer. But hear me out, because this isn't about being evasive or intellectually lazy. This is about the fundamental nature of time itself, about what it means for time to have a beginning, and about the limits of language and logic when we're trying to describe something as profoundly strange as the origin of the universe. We're going to explore why asking what happened before the Big Bang might be like asking what's north of the North Pole. It sounds like a perfectly reasonable question, but when you actually think about what the words mean, you realize it doesn't quite work the way you think it does. So let's start with the basics. When we talk about the Big Bang, we're talking about the moment when space-time came into existence. Not just space, not just matter, not just energy, but the entire four-dimensional fabric of space-time itself. Before the Big Bang, and I'm already using that word before in a way that's going to get me in trouble, there was no space. There was no time. There was no anything, at least not in any way that we can meaningfully describe with our current understanding of physics. Now, this is where most people's intuition completely breaks down, because we're so used to thinking about time as this universal, absolute thing. Time is like a river that flows steadily in one direction, carrying us along from the past through the present and into the future. That's how we experience time in our everyday lives, and it's a perfectly reasonable way to think about it for most purposes. But Einstein showed us over a century ago that time isn't actually like that at all. Time is part of space-time, this unified four-dimensional structure, and it can be warped and stretched and bent by the presence of mass and energy. Time is relative. It flows at different rates depending on how fast you're moving or how deep you are in a gravitational field. And here's the kicker. If time is part of space-time, and space-time came into existence at the Big Bang, then time itself came into existence at the Big Bang. Time has a beginning. It's not an eternal background against which events play out. It's a physical thing, part of the structure of the universe, and it started when the universe started. So when you ask what happened before the Big Bang, you're asking what happened before time existed. And that question, as sensible as it sounds, is actually incoherent. It's like asking what happened during the time when there was no time. The words form a grammatically correct sentence, but they don't actually refer to anything real. Stephen Hawking,
one of the greatest physicists of the 20th century, spent a lot of time thinking about this problem, and he came up with what I think is one of the most elegant explanations for why the question doesn't work. Hawking liked to use the analogy of the North Pole. Imagine you're standing on the surface of the Earth, and you start walking north. You can keep walking north for as long as you want, getting closer and closer to the North Pole. Eventually, you reach the North Pole itself, the northernmost point on Earth. Now, you might ask, what's north of the North Pole? And the answer is nothing. Not because there's some mysterious void, or because the Earth ends there, but because north stops meaning anything once you reach the North Pole. The concept of north is defined by the geometry of the Earth's surface and the orientation of its axis. And at the North Pole, you're literally at the point where north converges. There is no further north to go. The question is meaningless. Hawking argued that asking what happened before the Big Bang is exactly the same kind of meaningless question. The Big Bang is the boundary of time, the point where time begins. Just as there's nothing north of the North Pole, because north doesn't extend beyond that point, there's nothing before the Big Bang, because before doesn't extend back beyond that point. Time itself has a boundary, and that boundary is the Big Bang. This is what's known as the Hartle-Hawking no-boundary proposal, which Hawking developed along with James Hartle in the early 1980s. It's a model of the universe where time is finite in the past, but has no beginning in the sense of a sharp edge or boundary where things suddenly start. Instead, time smoothly transitions from a space-like dimension near the Big Bang to a time-like dimension as the universe evolves. I'll be honest, the mathematics of the no-boundary proposal are way beyond what we can get into here, and frankly, they're beyond what I fully understand without sitting down with a textbook and several pots of coffee. But the basic idea is beautiful in its simplicity. Near the Big Bang, the distinction between time and space becomes blurred. Time behaves more like a spatial dimension, which means the usual rules about cause and effect, about one moment following another, don't apply. And as the universe expands and cools, time gradually takes on the properties we're familiar with. It becomes the dimension along which events unfold in sequence. But right at the very beginning, at the Big Bang itself, time is just another direction in space-time, and asking what came before is like asking what's at the edge of the Earth's surface. There is no edge. The surface is finite, but unbounded. Now, Hawking himself put this idea in very poetic terms in his book A Brief History of Time, which, if you haven't read it, you absolutely should, because it's one of the best popular science books ever written. Hawking wrote, "The universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be." That's a profound statement. The universe just is. It exists. It doesn't need a cause in the traditional sense because causation requires time, and time only exists within the universe. Asking what caused the Big Bang is like asking what's causing time itself to flow. The question assumes there's some external framework, some larger context in which cause and effect operate, but there isn't. The universe is all there is. Now, I know what you're thinking, because it's what I thought when I first encountered this idea. Okay, fine. Time began at the Big Bang. There's no before in the usual sense. But surely something existed, right? Surely there was some kind of quantum state, some configuration of energy or fields or whatever that gave rise to the Big Bang. And you're not wrong to think that. In fact, a lot of physicists would agree with you. But here's the subtle part. even if there was some kind of pre-Big Bang state, some quantum fluctuation in a pre-existing vacuum or whatever, that state didn't exist in time as we understand it. It existed, if we can even use that word, in some more fundamental framework that we don't fully understand yet. And within that framework, our usual concepts of time and causality might not apply at all.
This gets at a really important distinction that I think often gets glossed over in popular discussions of cosmology. There's a difference between what physicists call cosmological time, which is the time measured by the expansion of the universe, and the kind of time we experience in our everyday lives, which is deeply tied to causality and the arrow of time, and the fact that we remember the past but not the future. Cosmological time is a coordinate, a way of labeling events in space-time. It's useful and it's measurable, but it's not fundamental in the way we intuitively think of time as fundamental. And near the Big Bang, where our theories break down and quantum effects dominate, cosmological time might not even be a well-defined concept. This is why some physicists argue that the question of what happened before the Big Bang isn't just unanswerable, it's literally meaningless. It's a category error, a misuse of language that stems from our inability to fully let go of our intuitive notions about how time works. We want there to be a before. We want there to be a sequence of events leading up to the Big Bang. Our brains are wired to think in terms of cause and effect, of one thing happening after another. But the universe doesn't owe us an explanation that fits neatly into those categories. Reality, at the most fundamental level, might just be weirder than our language can capture. But let's play devil's advocate for a second, because not every physicist agrees with Hawking's no-boundary proposal, or with the idea that the question is meaningless. There are alternative models, alternative ways of thinking about the origin of the universe that do allow for something before the Big Bang. Some of these models involve cyclic cosmologies, where the universe goes through repeated cycles of expansion and contraction, big bangs and big crunches, over and over again for eternity. In these models, our Big Bang wasn't the first, it was just the latest in an infinite series. And in that case, there absolutely was a before, even if that before was part of a previous cycle that's now causally disconnected from us. Other models involve the multiverse, this idea that our universe is just one bubble in an infinite froth of universes, each with its own Big Bang, its own laws of physics, its own history. In these models, there might be some larger meta-time, some higher dimensional temporal framework in which different universes are born and evolve and die. And within that framework, you could talk about what happened before our Big Bang in a meaningful way. Maybe our universe budded off from another universe. Maybe it was created by a quantum fluctuation in some pre-existing space. Maybe it's part of an eternal inflation scenario where new universes are constantly being spawned and the process has no beginning or end. These are all legitimate scientific ideas, and we're going to dive into them in much more detail in the next chapter. But here's the thing. Even in these models, you eventually run into the same problem. If the multiverse exists, where did it come from? If there's an eternal cycle of universes, did the cycle have a beginning, or has it been going on forever? And if it's been going on forever, what does that even mean? You can push the question back further and further, but eventually you hit a wall. Eventually you reach a point where the usual rules of cause and effect and temporal sequence break down, and you're left with the same fundamental mystery. Why is there something rather than nothing? Why does anything exist at all? Now, some philosophers and theologians have seized on this as evidence that science can't answer the ultimate questions, that there must be something outside the universe, some first cause or prime mover or God that brought everything into existence. And look, I'm not going to get into a debate about religion here. That's not what this is about. But I will say this. Inserting God or some other supernatural explanation at the point where our scientific theories run out doesn't actually solve the problem. It just relabels it. Because now you have to ask, where did God come from? What caused God? And if your answer is that God is eternal, that God exists outside of time and doesn't need a cause, well, why can't the universe itself be eternal, or exist outside of time, or not need a cause? You haven't actually explained anything. You've just added an extra layer of mystery. The physicist Lawrence Krauss has argued, somewhat controversially, that the universe can arise from nothing without any need for a creator, where nothing, in this context, means the quantum vacuum with all its weird properties that we talked about in the last chapter. And I think that's a reasonable position to take, as long as you're honest about what you mean by nothing. The quantum vacuum isn't philosophical nothing. It's not the complete absence of anything. It's a state with physical properties, with energy, with the laws of quantum mechanics governing its behavior. But it's the closest thing to nothing that actually exists in the natural world. And if the universe can arise from that, then in a very real sense, you've explained how you get something from nothing without invoking anything supernatural. But Krauss's argument has been criticized by philosophers, most notably David Albert, who pointed out that the quantum vacuum isn't really nothing. It's a highly structured something with specific properties that themselves require explanation. And that's a fair criticism. The quantum vacuum doesn't just exist for no reason. It exists because the laws of physics are what they are, because quantum mechanics works the way it does. So the question just shifts from why is there a universe to why are there laws of physics? Why does quantum mechanics exist? Why is the universe governed by these particular laws and not some other laws? And this is where we really do reach the limits of what science can currently tell us. We can describe how the universe evolved from the Big Bang to the present with remarkable precision. We can trace the history back to fractions of a second after the Big Bang and make detailed predictions about what we should observe, predictions that have been confirmed over and over again. We can even make educated guesses about what happened during inflation and how quantum fluctuations in the vacuum might have seeded the structure we see today. But when you ask why the laws of physics are what they are, or why there's anything at all rather than nothing, science doesn't have an answer. Not yet, anyway. Maybe not ever. Some physicists think we'll eventually find a theory of everything, some ultimate set of equations that describes all the fundamental forces and particles and explains why the universe has the properties it does. Maybe string theory will turn out to be that theory, or maybe it'll be something we haven't even thought of yet. But even if we find such a theory, it won't answer the question of why that theory is true. Why those equations and not some other equations? You can always ask one more why. It's turtles all the way down, as the old saying goes. And maybe that's okay. Maybe there are some questions that don't have answers. Not because we're not smart enough, or because our technology isn't advanced enough, but because the questions themselves are hitting up against the fundamental limits of what can be known or described. Maybe the universe just is, as Hawking said. Maybe it exists as a brute fact, and any attempt to explain that fact in terms of something more fundamental is doomed to fail, because there is nothing more fundamental. Or maybe not. Maybe we're just scratching the surface. Maybe future generations of physicists will look back on our current theories the way we look back on Newton's laws, as a useful approximation that works in a certain regime but misses the deeper truth. Maybe there is something before the Big Bang, some pre-existing state or framework that we haven't discovered yet.
maybe time itself is an illusion, an emergent property of some more fundamental structure that exists outside of time.
These ideas sound crazy, and maybe they are crazy, but science has a long history of proving that reality is much stranger than anyone imagined. The point I'm trying to make here is that when we ask what happened before the Big Bang, we're not just asking a scientific question. We're also asking a philosophical question about the nature of time, the limits of explanation, and what it even means for something to exist. And those are deep questions, questions that have occupied some of the greatest minds in history, and we're not going to solve them definitively in this video, or probably in our lifetimes. But that doesn't mean they're not worth thinking about.
It doesn't mean we should just shrug our shoulders and give up. Because here's the thing. Even if the question is meaningless in a strict logical sense, even if there is no before the Big Bang in the way we usually think about time, that doesn't mean there's nothing interesting to say. It doesn't mean the story ends there. Because while our universe might have had a beginning, that doesn't mean it's the only universe. It doesn't mean the Big Bang was a singular, unique event. There are models, perfectly respectable scientific models, that suggest our universe is just one of many, that the Big Bang was just one episode in a much larger cosmic story.
And in those models, you can talk about what else exists, even if you can't talk about what came before in a temporal sense. This is where the conversation shifts from the philosophical question of before to the scientific question of beyond. Instead of asking what happened before our Big Bang, we can ask what else is out there. Are there other universes? Is our universe part of a larger multiverse? Did our universe emerge from some pre-existing structure? And if so, what was that structure and what are its properties? These questions are answerable, at least in principle.
They might not be testable with a more current technology, but they're grounded in real physics and real mathematics, and they open up possibilities that are just as mind-blowing as anything we've talked about so far. And that's where we're headed next. We're going to explore the multiverse, this idea that our universe is just one bubble in an infinite sea of universes. We're going to talk about cyclic models, where universes are born and die and are reborn in an eternal cosmic rhythm. We're going to look at models where the Big Bang wasn't a beginning, but a transition, a phase change from some previous state. And we're going to see how all of these ideas fit together into a larger picture of reality that's so vast and so strange that it makes our universe, with its hundreds of billions of galaxies and its 13.8 billion year history, look like a tiny, insignificant speck. Because if there's one lesson we've learned from cosmology over the past century, it's that the universe is always bigger and stranger than we thought. Every time we think we've figured out the whole picture, every time we think we've reached the edge of what's possible or the limit of how weird things can get, reality surprises us.
We thought the Milky Way was the entire universe, and then we discovered there were billions of other galaxies. We thought the universe was static and eternal, and then we discovered it was expanding and had a beginning. We thought matter was all there was, and then we discovered dark matter and dark energy. So why should we think we've reached the end now? Why should we assume that our universe, the one we can see and measure, is all there is? The answer is we shouldn't. And the fact that we can even ask these questions, that we can use the tools of mathematics and physics to explore possibilities beyond what we can directly observe, is one of the most remarkable things about being human.
We're pattern-seeking, storytelling creatures, and the biggest story of all is the story of where we came from and what else is out there. So let's keep going. Let's push beyond the boundary of our universe and see what lies beyond. All right, so we've just spent the last chapter wrestling with this deeply uncomfortable philosophical question about whether it even makes sense to ask what happened before the Big Bang, whether the word before has any meaning when time itself came into existence at that moment, and whether we're just asking the cosmic equivalent of what's north of the North Pole. And look, I get it. That's frustrating. It feels like we're hitting a wall, like we've reached the edge of what we can know or even ask. But here's the thing. Even if the question of what came before our Big Bang is incoherent in a strict temporal sense, that doesn't mean the story ends there. Because while our universe might have had a beginning, that doesn't necessarily mean it's the only universe. It doesn't mean the Big Bang was a singular, unique event with nothing before it and nothing outside it.
There are models, perfectly respectable scientific models, grounded in real physics and real mathematics, that suggest our universe is just one small part of a much larger reality. One piece of a cosmic puzzle that's so vast it makes our entire observable universe look like a single grain of sand on an infinite beach. This is where we need to shift our thinking. Instead of asking what came before our Big Bang, we can ask what else is out there. Are there other universes? Is our Big Bang just one of countless Big Bangs happening all the time in some larger structure? Did our universe bud off from something else, some pre-existing cosmic framework that's been around far longer than the 13.8 billion years since our particular Big Bang occurred? These questions might sound like science fiction, and honestly, some of them are pretty wild, but they're grounded in legitimate physics, in extensions of theories that we've already tested and confirmed in other contexts, and they open up possibilities that are just as mind-blowing as anything we've talked about so far. Let's start with the multiverse, because this is probably the most talked about idea in modern cosmology, and also one of the most controversial. The basic concept is simple enough. Our universe, the one we can see and measure, is not the only universe. It's just one bubble in an infinite foam of universes, each with its own Big Bang, its own history, its own laws of physics, possibly even its own values for fundamental constants like the speed of light or the strength of gravity. These other universes exist, but they're so far away or so causally disconnected from us that we can never interact with them or observe them directly. They're out there, doing their thing, completely independent of us. Now, before you roll your eyes and dismiss this as pure speculation, let me be clear. The multiverse idea didn't come from science fiction writers or philosophers smoking too much weed. It came from taking our best theories of physics, theories that have been tested and confirmed in countless experiments, and following them to their logical conclusions. The multiverse isn't something physicists invented because they thought it would be cool. It's something that fell out of the math when they were trying to solve other problems. And in particular, it fell out of the theory of cosmic inflation, which we talked about a few chapters ago. Remember inflation? That brief period in the first fraction of a second after the Big Bang, when the universe expanded exponentially, doubling in size over and over again in an incredibly short time, solving the horizon problem and the flatness problem, and explaining where all the structure in the universe came from? Well, it turns out that once you start inflation, it's really hard to stop it everywhere at once. The guy who first proposed inflation, Alan Guth, realized this pretty early on, back in the 1980s. He called it the eternal inflation problem, and here's how it works. During inflation, the universe is driven by this inflaton field sitting in a high energy state, what physicists call a false vacuum. The false vacuum has this property where it creates negative pressure, causing space to expand exponentially. But eventually, the inflaton field decays to a lower energy state, the true vacuum, and inflation ends. The energy gets released, particles get created, and you end up with the hot, dense state we call the Big Bang. That's what happened in our region of space 13.8 billion years ago. But here's the catch. The decay from false vacuum to true vacuum doesn't happen everywhere at once. It happens randomly through quantum fluctuations. One region decays and inflation ends there. But while that's happening, the regions that haven't decayed yet are still inflating, still doubling in size over and over, creating more and more space. So what you end up with is this picture where inflation starts in one region and then little bubbles of true vacuum start forming inside the inflating false vacuum. Each bubble is a universe where inflation has ended and normal expansion has begun. But between the bubbles, the false vacuum is still inflating, creating more space, and more bubbles are constantly forming inside that space. It's like boiling water. You get bubbles forming all over the pot, but the water between the bubbles is still boiling, and more bubbles keep appearing. Except in this case, the pot is infinite. It's been boiling forever, and it will keep boiling forever. Inflation becomes eternal. It never truly ends. It just ends in certain pockets, and each pocket becomes a universe. Our universe is one of those pockets, one of those bubbles. And according to eternal inflation, there are infinitely many other bubbles out there, each one a separate universe with its own Big Bang, its own history. Some of those universes might look a lot like ours. Some might be completely different, with different values for the fundamental constants, different particles, different forces, maybe even different numbers of dimensions. And all of this is a natural consequence of inflation, which we have good reasons to believe actually happened based on observations of the cosmic microwave background. This is what's called the inflationary multiverse, or sometimes the bubble universe model, and it's probably the most well-developed and widely accepted version of the multiverse idea among physicists. It's not proven, obviously. We can't directly observe other universes because they're outside our cosmic horizon, beyond the reach of any signal that could ever get to us. But it's a logical prediction of a theory that we have other reasons to believe is correct, and that makes it worth taking seriously. Now, there are other versions of the multiverse idea that come from different areas of physics. One of the most famous, or infamous, depending on who you ask, is the many worlds interpretation of quantum mechanics. This is a completely different beast from the inflationary multiverse, and it's worth spending a minute on it because it gets brought up a lot and often gets confused with the cosmological multiverse we were just talking about. The many worlds interpretation was proposed by Hugh Everett back in 1957 as a way to solve one of the deepest mysteries in quantum mechanics, the measurement problem. In standard quantum mechanics, particles exist in a superposition of multiple states until you measure them, and then the superposition collapses and you get one definite outcome. Like Schrödinger's famous cat, which is both alive and dead until you open the box and look. But what causes the collapse? What makes the universe pick one outcome over another? Nobody really knows, and it's been a philosophical headache for nearly a century. Everett's idea was radical. What if the collapse never happens? What if every possible outcome of every quantum measurement actually occurs, but in different branches of reality? When you measure a particle's position, the universe splits into multiple copies. In one copy, you measure the particle here. In another copy, you measure it there. Both outcomes are real. Both versions of you exist, but you can't communicate with each other because you're in different branches of the wave function. The universe is constantly branching, splitting into more and more copies with every quantum event. And all of these branches exist in this vast, infinite dimensional space called Hilbert space. This is wild, and a lot of physicists hate it because it seems so extravagant. You're saying that every time a quantum event happens, the entire universe duplicates itself? That seems like a huge violation of Occam's razor, the principle that you should prefer the simplest explanation that fits the data. But proponents of many worlds argue that it's actually simpler in a certain sense, because you don't need to add any extra rules about when or how the wave function collapses.
You just let the Schrödinger equation do its thing, and the branching happens automatically. You don't need a special role for observers or consciousness or measurement devices. It all follows from the math. Now, here's the important thing. The many worlds interpretation and the inflationary multiverse are two completely different ideas. The many worlds interpretation is about quantum mechanics and how to interpret what happens when you make a measurement. The inflationary multiverse is about cosmology and what happens when you have eternal inflation creating separate regions of spacetime. They're not mutually exclusive.
You could have both. A multiverse of bubble universes, where each bubble itself is constantly branching into many worlds. Or you could have one without the other. They're separate issues, and they come from separate areas of physics. But they both suggest that our universe is just one part of a much larger reality, and I think that's fascinating. There's also this idea from string theory called the landscape multiverse, and this one's worth mentioning, even though string theory itself is controversial and hasn't been proven.
String theory, for those who aren't familiar, is this attempt to unify quantum mechanics and general relativity by proposing that the fundamental building blocks of reality aren't point particles, but tiny vibrating strings. Different vibration patterns of the strings correspond to different particles. It's elegant, it's mathematically beautiful, but it's also incredibly complicated and makes predictions that are currently untestable because the scales involved are so tiny. One of the big problems with string theory is that there isn't just one version of it. There are something like 10 to the 500th power different possible configurations, different ways the extra dimensions that string theory requires can be curled up. And each configuration gives you a different set of physical laws, different particles, different forces, different values for the constants of nature. This vast space of possibilities is called the string theory landscape, and if eternal inflation is correct, all of these possibilities might be realized somewhere in the multiverse. Different bubble universes might correspond to different points in the landscape, each one with its own unique physics.
This idea has been used to explain something called the fine-tuning problem, which is the observation that the constants of nature in our universe seem to be finely tuned for the existence of life. Change the strength of gravity by a tiny amount, or change the mass of the electron by a small fraction, and stars can't form, or atoms can't exist, or chemistry doesn't work, and life as we know it becomes impossible. Why are the constants just right? One answer is the anthropic principle. They're just right because we're here to observe them. In a multiverse with infinitely many bubble universes, each with different constants, most of them will be lifeless.
But some tiny fraction will have constants in. All right, so we've spent the last several chapters diving deep into the physics of the early universe, exploring quantum vacuums and cosmic inflation and the cosmic microwave background, venturing into the philosophical territory of whether the question of what came before the Big Bang even makes sense, and then opening up this mind-bending possibility that our universe might be just one bubble in an infinite foam of universes, or one cycle in an eternal cosmic rhythm. We've gone from the smallest possible scales, the Planck length, to the largest conceivable structures,
infinite multiverses stretching beyond anything we can ever hope to observe.
And through all of this, we've been circling around this one fundamental question, the question that started this whole journey, the question that every human being who's ever looked up at the night sky has asked at some point in their lives. Why is there something rather than nothing? Why does anything exist at all? This is the grand enigma, the ultimate mystery, the question that sits at the intersection of physics and philosophy, and maybe even theology, though we're going to try to stay in the realm of science as much as we can. Because here's the thing. We've explained a lot in this video. We've explained how the universe evolved from a hot, dense state to the vast cosmos we see today.
We've explained how cosmic inflation solved the horizon and flatness problems. We've explained how quantum fluctuations in the vacuum got stretched out and became the seeds for galaxies. We've even explained, or at least proposed, how the universe might have emerged from a quantum vacuum through a process that doesn't require anything supernatural or magical. But explaining how the universe came to be is not the same as explaining why the universe came to be. And that why question, that's the one we haven't really tackled head-on yet. That's the one we need to grapple with now. So let's start by being really clear about what we're asking.
When we ask why there is something rather than nothing, we're not asking for a mechanism. We've already covered the mechanisms. We know how inflation works, at least in broad strokes. We know how particles can pop out of the quantum vacuum. We know how false vacuum decay can trigger exponential expansion. The how is well established, or at least well theorized. What we're asking is more fundamental. We're asking why those laws of physics exist in the first place. Why is there a quantum vacuum with specific properties that allow it to fluctuate and spawn universes? Why is there a Schrödinger equation governing the behavior of quantum fields? Why are there four fundamental forces with the particular strengths they have? Why is the speed of light exactly 299,792,458 meters per second and not some other value? Why is the universe the way it is and not some other way? And this is where we hit what I think is one of the most profound realizations in all of physics. The universe we live in is incredibly finely tuned. Now, when I say finely tuned, I don't mean that in any sort of mystical or religious sense, at least not necessarily. I mean it in a very specific technical sense. The fundamental constants of nature, the numbers that appear in our equations and determine how particles interact and how forces behave, they have very specific values. And if those values were even slightly different, like a fraction of a % different in some cases, the universe would be a radically different place. Stars wouldn't form, atoms wouldn't be stable, chemistry wouldn't work. Life, at least life as we know it, would be completely impossible. Let me give you some examples, because this stuff is genuinely mind-blowing when you actually look at the numbers. Take the strength of gravity. Gravity is by far the weakest of the four fundamental forces. It's something like 10 to the 38 times weaker than the electromagnetic force, which is why a tiny fridge magnet can overcome the gravitational pull of the entire Earth when it picks up a paperclip. But if gravity were just slightly stronger, like a few % stronger, stars would burn through their fuel much faster. The sun would have exhausted its hydrogen billions of years ago, long before life had a chance to evolve on Earth. On the other hand, if gravity were slightly weaker, stars might never ignite at all. You need a certain amount of gravitational pressure to squeeze hydrogen atoms together hard enough to start fusion, and if gravity's too weak, you don't get there. Or take the strong nuclear force, the force that holds quarks together inside protons and neutrons.
and holds protons and neutrons together inside atomic nuclei. If the strong force were about 5% weaker, you couldn't form any elements heavier than hydrogen. Protons wouldn't stick together, so deuterium wouldn't form. And without deuterium, you can't build up to helium and carbon and oxygen and all the other elements that make up planets and people. The universe would just be hydrogen and nothing else. On the flip side, if the strong force were about 5% stronger, you'd have a different problem. The diproton, two protons stuck together without any neutrons, would be stable.
And if that were the case, all the hydrogen in the early universe would have fused into diprotons and heavier elements almost immediately. There'd be no hydrogen left over, which means no water, no organic chemistry, no life. Then there's the electromagnetic force, which determines how charged particles interact with each other. If you tweak that force by a small amount, atoms would behave completely differently. Electrons might not bind to nuclei in stable orbits. Chemical bonds might not form. Or maybe they'd be so strong that molecules couldn't break apart and rearrange, which means no chemical reactions, no metabolism, no life. The entire structure of chemistry depends on the electromagnetic force having exactly the strength it does. And it's not just the forces. The masses of fundamental particles are also finely tuned. The electron, for example, has a mass that's about 1,800 times lighter than a proton. If the electron were heavier, atoms would be smaller and chemical bonds would be weaker. If it were lighter, atoms would be bigger and less stable. The ratio between the electron mass and the proton mass seems arbitrary, like it could have been anything. But it turns out that only a narrow range of values allows for stable atoms and complex chemistry.
Then there's the cosmological constant, or dark energy, which we've mentioned a few times already. This is the energy density of empty space, and it's responsible for the accelerating expansion of the universe. We measure it today, and it has this incredibly tiny value, something like 10 to the negative 122 in natural units. That's a decimal point followed by 121 zeros and then a 1. It's absurdly small. But if it were much larger, even by a factor of a few, the universe would have expanded so fast that galaxies and stars never would have formed. Matter would have been pulled apart before gravity could clump it together. And if the cosmological constant were negative instead of positive, the universe would have collapsed back on itself billions of years ago. The fact that it's positive and tiny is essential for a universe that can host life. Now, when you add all of this up, when you look at all the different parameters that have to be just right, you start to get this picture of a universe that's balanced on a knife's edge. Change any one of a dozen fundamental constants by a small amount, and you get a universe that's radically different. A universe where complexity never emerges, where stars don't form, where atoms don't exist, where life is impossible.
This is what physicists call the fine-tuning problem, and it's one of the deepest puzzles in cosmology. There are basically three ways to respond to the fine-tuning problem. The first response is to say it's just a coincidence. The constants happen to have the values they do, and we happen to exist, and there's no deeper explanation. This is a perfectly valid position to take, but it's not very satisfying. It feels a bit like saying the universe won the cosmic lottery, which it did, but it doesn't explain why there was a lottery in the first place, or why the winning ticket happened to get drawn.
The second response is to invoke some kind of designer or creator, some intelligence that deliberately chose the constants to allow for life. This is the argument from intelligent design, and it's popular in some religious circles. If the universe looks like it was designed to support life, maybe that's because it was designed.
Now, I'm not going to get into a debate about the existence of God here because that's way beyond the scope of this video, and frankly beyond the scope of science. Science deals with natural explanations, with things we can test and observe and measure. Once you invoke a supernatural designer, you've left the realm of science and entered the realm of faith.
And there's nothing wrong with faith, but it's not what we're doing here. And besides, invoking a designer just pushes the question back one step. Who designed the designer? Where did God come from? You haven't actually solved the problem, you've just relabeled it. The third response, and this is the one that most physicists who think about this stuff seriously tend to favor, is the anthropic principle. The idea is actually pretty simple once you get past the jargon. The anthropic principle says that the universe must have properties that allow for the existence of observers, because if it didn't, there'd be nobody around to observe it and ask why. It's a selection effect.
We observe a finely tuned universe because only a finely tuned universe can produce observers like us. In any universe where the constants were different and life couldn't exist, there'd be nobody there to notice or care. Now, the anthropic principle by itself doesn't explain anything. It's just a tautology. Of course we find ourselves in a universe that allows us to exist. Where else would we be? But the anthropic principle becomes genuinely explanatory when you combine it with the multiverse idea we talked about in the last chapter.
If there are infinitely many universes, each with different values for the fundamental constants, then some of them will have the right values for life, and most of them won't. We find ourselves in one of the rare life-friendly universes, not because ours is special, but because those are the only universes where anyone can exist to ask the question. It's like asking why you were born on a planet with liquid water and breathable air. It's not that Earth is the only planet in the universe, it's that you couldn't have been born on a planet without water and air, because life requires those things. Same logic applies to the universe as a whole.
This is an elegant solution to the fine-tuning problem, and it doesn't require any supernatural explanations or cosmic coincidences. But it does require the multiverse to be real, and as we discussed, the multiverse is hard to test directly because, by definition, we can't observe other universes. So we're left in this uncomfortable position where the best explanation we have for why the universe is the way it is depends on the existence of things we can never see or measure. That bothers a lot of people, and honestly, it bothers me too. Science is supposed to be about testing hypotheses, about making predictions that can be confirmed or ruled out by observations.
And the multiverse doesn't really give us that. It's more of a philosophical framework than a testable scientific theory. But here's the thing, and I think this is really important to emphasize. Just because we can't test the multiverse directly doesn't mean it's not a valid scientific idea. Lots of things in science are hard or impossible to observe directly, but we infer their existence from other evidence. We can't see black holes directly, at least not the singularity at their center, but we know they exist because of how they affect nearby matter and light. We can't see dark matter. It doesn't emit or absorb light, but we know it's there because of its gravitational effects on galaxies. We've never directly observed quarks in isolation. They're always confined inside protons and neutrons, but we know they exist because of particle physics experiments. The multiverse is in a similar category. If it's a natural prediction of theories that we have other reasons to believe are correct, like cosmic inflation, then it's worth taking seriously, even if we can't test it directly. And there's another angle to this whole fine-tuning discussion that I think is worth bringing up because it relates to something we talked about way back in the first chapter. Maybe the constants aren't as arbitrary as they seem. Maybe there's some deeper theory, some theory of everything that we haven't discovered yet,
that explains why the constants have the values they do. Maybe the constants are mathematically related in some way we don't understand, such that once you fix one of them, all the others are determined. Maybe there's only one logically consistent set of physical laws, and we just happen to live in the universe where those laws apply because that's the only universe that can exist. This is essentially the dream of string theory and other attempts at unification.
The idea is that at some fundamental level, all of physics is described by a single elegant equation or a single mathematical structure, and all the messiness we see, all the different particles and forces and constants, they're just different manifestations of that one underlying reality. If that's true, then maybe the fine-tuning problem goes away. Maybe the universe has to be the way it is, because any other configuration would be mathematically inconsistent. The constants have the values they do, not because of random chance or divine intervention or anthropic selection, but because those are the only values that make mathematical sense. This is a beautiful idea, and it's motivated a lot of research over the past few decades. But so far, we don't have that theory of everything. String theory hasn't panned out the way people hoped it would. It's mathematically rich, and it's made some interesting predictions, but it hasn't given us the definitive answer, and it's not clear if it ever will. Maybe there is no theory of everything. Maybe the universe really is just a set of arbitrary constants that happen to have the values they do, and will never have a deeper explanation than that. Or maybe the multiverse is real, and the constants vary from universe to universe, and we're just in one of the lucky ones. Or maybe there's some completely different explanation that nobody's thought of yet. And this brings us back to the question we started with. Why is there something rather than nothing? And I have to be honest with you, I don't have a satisfying answer to that question. Nobody does. Science can tell us how the universe evolved from the Big Bang to the present. It can tell us how quantum fluctuations in the vacuum might have given rise to inflation and ultimately to everything we see. It can even give us plausible scenarios for how the universe could have emerged from what looks like nothing, from the quantum vacuum with all its weird properties. But it can't tell us why there's a quantum vacuum in the first place. It can't tell us why the laws of physics exist. It can't tell us why there's something rather than nothing in the most fundamental sense. Some physicists think this is a question that science will never be able to answer, that we've reached the limits of what empirical investigation can tell us. Once you get to the most fundamental level, to the laws of nature themselves, there's nowhere further to go. You can't explain the laws of nature in terms of something more fundamental, because by definition, there is nothing more fundamental. The laws just are. They exist as brute facts about reality, and any attempt to explain them is doomed to infinite regress. You explain the laws in terms of some deeper principle, and then you have to explain the deeper principle in terms of something even deeper, and it never ends. At some point, you just have to accept that there are things that simply are, things that don't have explanations in terms of anything else. Other physicists are more optimistic. They think we just haven't figured it out yet, that future generations will look back on our current puzzlement the way we look back on pre-Newtonian physics. Maybe there is a theory of everything. Maybe we'll discover it in 50 years, or 100 years, or 1,000 years. Maybe it'll explain why the laws are what they are, why the constants have the values they do, why the universe exists at all. Maybe it'll even explain why that theory is true and not some other theory. I don't know if that's possible, but I'd like to think it is. I'd like to think that we haven't reached the end of the road, that there are still deeper truths waiting to be uncovered. And this is where I think we need to talk about the future, about where cosmology goes from here.
Because even though we've made incredible progress over the past century, there's still so much we don't know.
The fine-tuning problem is unsolved. The nature of dark matter is unknown. Dark energy is a complete mystery. We don't have a theory of quantum gravity. We don't know if the multiverse is real. We don't know what happened at the moment of the Big Bang, at time zero, when our equations break down. These are massive open questions, and they're going to require new observations, new experiments, new theoretical frameworks to answer. On the observational side, we're building more powerful telescopes that can look further back in time, closer to the Big Bang, and see fainter and more distant objects. The James Webb Space Telescope, which launched in 2021, is already sending back images of galaxies that formed just a few 100 million years after the Big Bang, galaxies we could never have seen with previous instruments. And there are even more ambitious projects in the works, telescopes that will be able to see even further, even fainter, even closer to the beginning. We're also getting better at studying the cosmic microwave background. Experiments like the Planck satellite have mapped the CMB with exquisite precision. But there are still subtle features that haven't been measured yet, features that could tell us about inflation and quantum gravity and the very first moments of the universe. And then there are gravitational waves, ripples in space-time caused by violent cosmic events like colliding black holes or the Big Bang itself. We've only just started detecting gravitational waves in the past decade with experiments like LIGO and Virgo, but there are plans for space-based detectors that will be able to see gravitational waves from the early universe, waves that were produced during inflation and have been traveling through space ever since. If we can detect those primordial gravitational waves, it would be direct evidence that inflation happened and would tell us about the energy scale at which it occurred. That would be one of the biggest discoveries in the history of cosmology. On the theoretical side, physicists are still working on that elusive theory of quantum gravity. String theory is one approach, loop quantum gravity is another, and there are other ideas floating around too. We don't know which one is right, or if any of them are right, but the work continues. And every once in a while, there's a breakthrough, some new insight or mathematical technique that opens up possibilities we hadn't considered before. Progress in theoretical physics is slow, but it does happen. We're understanding more and more about how the universe works at the deepest levels, even if we're not quite there yet. But here's the thing, and I think this is what makes this whole subject so fascinating. Even if we answer all the scientific questions, even if we figure out quantum gravity and dark matter and dark energy and the multiverse and everything else, we might still be left with that fundamental mystery. Why is there something rather than nothing? Because that question isn't just a scientific question. It's a philosophical question, maybe even a spiritual question, depending on how you look at it. It's a question about the nature of existence itself, about why anything exists at all, and that might be beyond the reach of science. Science is incredibly powerful. It's given us an understanding of the universe that would have seemed like magic to people just a few centuries ago. But science has limits. It can tell us how things work, but it might not be able to tell us why things are. And maybe that's okay. Maybe some questions don't have answers, at least not answers that we can access with the tools of science. Maybe the universe just is, as Stephen Hawking said. It exists, and it doesn't need a reason or a cause or an explanation. It's a brute fact of reality, the ultimate given. And our job as curious humans is not to explain why it exists, but to explore it, to understand it, to marvel at it,
and to appreciate the fact that we're here, improbably, briefly, in this one corner of space and time, able to ask these questions and ponder these mysteries. Because that's the real miracle, isn't it? Not just that the universe exists, but that we exist. That out of the quantum vacuum and the Big Bang and billions of years of cosmic evolution, there emerged stars and planets. And eventually, on at least one small rocky world orbiting an unremarkable star in an ordinary galaxy, there emerged life. And that life became complex, became conscious, became curious. And now here we are, descendants of stardust, products of the Big Bang, asking where we came from and why we're here and what it all means. We don't have all the answers. We might never have all the answers, but we've come so far. We've traced the history of the universe back to fractions of a second after its beginning. We've mapped the cosmic microwave background, the afterglow of creation. We've measured the expansion rate and the age and the composition of the cosmos with remarkable precision. We've developed theories that explain how quantum fluctuations became galaxies, how nothing became something, how a universe emerged from what appears to be a vacuum. That's an incredible achievement. That's something to be proud of. And the quest continues. Every year we learn something new. Every decade brings breakthroughs that reshape our understanding. The grand enigma, the question of why there is something rather than nothing, it remains unsolved. But the fact that we can ask it, the fact that we've made as much progress as we have in understanding the answer, that's a testament to human curiosity, to our drive to explore and discover and make sense of the world around us. We might never fully solve the mystery. The universe might always hold secrets that are beyond our reach. But that doesn't mean we stop trying. That doesn't mean we stop looking up at the night sky and wondering. Because in the end, that's what makes us human. That's what makes this whole journey worthwhile. So here we are. We started this whole journey trying to answer one simple question. What existed before the Big Bang? And if you've made it this far, you've probably realized that the answer isn't simple at all. In fact, the answer might be that the question itself doesn't quite work the way we think it does. Because when you dig deep enough into the physics, when you really try to wrap your head around the nature of time and space and quantum mechanics and all the rest, you start to realize that our everyday intuitions about how reality works, they just don't apply at the most fundamental levels. Time had a beginning. Space came into existence. And asking what came before that is like asking what's north of the North Pole. The words make sense individually, but strung together, they point to something that doesn't exist. But here's what gets me. Even if we can't answer the question of what came before, even if that question turns out to be meaningless in a strict logical sense, we've still learned something profound. We've learned that nothing isn't what we thought it was. The quantum vacuum, the closest thing to true nothingness that exists in nature, is actually a seething cauldron of activity, a place where particles pop in and out of existence, and energy fluctuates, and the fabric of space-time itself becomes this chaotic foam at the smallest scales. We've learned that the universe might be just one bubble in an infinite multiverse, one cycle in an eternal cosmic rhythm, one story among countless others. We've learned that the laws of physics, the constants of nature, they're finely tuned in ways that seem almost miraculous, and we don't know why. We've learned that reality is stranger, deeper,
and more mysterious than anyone imagined.
And maybe that's the real point. Maybe the question of why there's something rather than nothing isn't one we're meant to answer. Maybe it's one we're meant to keep asking. Because in asking it, we're doing something uniquely human. We're reaching beyond ourselves, beyond our immediate experience, trying to make sense of the biggest mystery there is. And even if we never fully solve it, even if the universe always holds secrets that are just out of reach, that doesn't diminish what we've accomplished. It doesn't make the journey any less worthwhile. Because the universe exists. We exist.
And for a brief moment in cosmic time, we get to look up at the stars. We get to study the cosmic microwave background. We get to build particle accelerators and space telescopes and mathematical models. And we get to ask these questions. Why are we here? Where did we come from? What does it all mean? And maybe, just maybe, the fact that we're here asking those questions is the most remarkable thing of all.